Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight we're setting our sights on something quietly enormous, a kind of hidden landscape that stretches across hundreds of millions of light years. It's the strange possibility that our entire galaxy, our whole neighbourhood of stars, might be floating inside a cosmic hole. Not a black hole, not a danger to swallow worlds, but a vast, faintly glowing emptiness, known to astronomers as the KBC Void. The thought sounds dramatic at first, but the story of this invisible place is one of slow discovery, gentle questioning, and the delicate art of measuring almost nothing at all. So before we begin wandering through that emptiness together, take a moment to notice the space around you, the quiet between sounds, the small stillness where everything seems to pause. Because in a sense that's where tonight's story begins, not in chaos or collision, but in calm. You might have looked up at the night sky and felt that it was full, bursting with stars, galaxies, and glowing dust. But that fullness is deceiving. The universe, when you measure it honestly, is mostly empty. Between every cluster of galaxies lies an expanse so wide that light can spend hundreds of millions of years crossing it. These regions are called cosmic voids. They aren't truly empty. A few lonely galaxies drift through them, but compared to the crowded regions of the universe, they are astonishingly sparse. Imagine walking through a vast city where the lights of the buildings grow farther apart until they vanish, leaving only a faint glow on the horizon. That's roughly what a void would look like if you could see it from outside. And according to a growing body of evidence, our galaxy might sit right in the middle of one. The discovery of this possibility didn't happen overnight. In the early years of mapping the universe, astronomers believed galaxies were scattered more or less evenly through space, but as instruments improved, they began to notice patterns, enormous filaments and sheets where galaxies gathered like threads of glowing silk. Between those threads were empty regions, like pockets of air in a loaf of bread. One of those pockets turned out to be suspiciously close to home. The researchers who noticed it were Ryan Keenan, Amy Barger and Lennox Cowie, their initials forming the name KBC. When they published their findings in the 2010s, the idea was as simple as it was unsettling. They suggested that our galaxy and its neighbours might reside in a region hundreds of millions of light years wide that contained far less matter than the cosmic average. In other words, we might live inside a bubble. The word void tends to sound bleak, but astronomically it's more subtle. A void is not a complete absence of matter. It's a region where the density is lower than average, sometimes by 30, 40 or 50%. There are still galaxies, stars and planets inside, just fewer of them. The light that travels through such a region stretches differently as the universe expands, and that subtle distortion can be measured. It's not something we can see with the naked eye. It's more like feeling a slight change in the air pressure, the faint suggestion that something vast is missing. Detecting the absence requires patience, precision, and a willingness to listen to silence. Imagine trying to understand the shape of a dark room by the echoes of your own footsteps. That's what astronomers do when they study voids. They observe the light from thousands of galaxies, measure how far away each one is, and then look for patterns, the places where the light clusters, and the places where it thins out. The result is a three-dimensional map of the universe, like a web stretching in every direction. The threads of the web are galaxy clusters and filaments. The holes in between are voids, and in that vast cosmic web, one of the largest gaps seems to surround our own position. When you hear that we live inside a cosmic void, it's easy to imagine something dramatic, perhaps a dark sphere encasing our galaxy, cutting us off from the rest of the cosmos. But that's not quite right. The edges of the KBC Void aren't sharp. They blur gently into denser regions, and our galaxy sits somewhere near the centre. Not isolated, but floating in a slightly thinner patch of cosmic soup. It's like being in a part of the ocean where the water is a little less salty, or a little warmer. You wouldn't notice it unless you measured carefully, and yet, that slight difference could have enormous consequences for how we interpret the universe. One of those consequences involves the expansion of the cosmos itself. Astronomers measure how fast distant galaxies are moving away from us using something called the Hubble constant. It's a number that describes how quickly space stretches with distance. But over the years, scientists have found a puzzling disagreement. When they measure the Hubble constant using the cosmic microwave background, the ancient light left over from the Big Bang, they get one number. When they measure it using nearby galaxies and supernovae, they get a slightly higher number. The difference is small, but it's persistent. It's called the Hubble tension, and it has caused more than a few sleepless nights in cosmology. Here's where the KBC Void enters the picture. If we happen to live in a region of the universe that's less dense than average, then local galaxies would drift away from us slightly faster than expected. It's not because the universe as a whole is expanding faster, but because there's less gravitational pull in our neighbourhood, space itself would be stretching a little more freely. That could make the nearby measurements of the Hubble constant appear higher than those based on the cosmic average. In other words, our cosmic whole might be subtly warping our view of how the universe grows. It's a humbling thought. For centuries, humans have looked outward, assuming that what we see from here represents the universe as it truly is. But if we're living inside a vast underdense region, our perspective might be skewed, like trying to judge the shape of the Earth while standing in a deep valley. To correct for that, astronomers have to model the void, account for its effects, and see whether the numbers line up. Some simulations suggest the KBC Void could indeed explain at least part of the discrepancy. Others argue it's not quite enough. The debate continues quietly, like a long chess match played across light years. Yet beyond the numbers, there's something strangely comforting about the idea. The notion that we might inhabit a giant cosmic bubble fits neatly with what we already know about the universe's structure. Space isn't uniform, it's patchy, textured, dynamic. Galaxies gather in clusters, and those clusters link together in vast chains, leaving empty spaces between them. If you could drift far enough from one cluster to another, you'd pass through those empty regions, silent, faintly glowing, almost featureless. And if our own galaxy happens to rest in one of those spaces, it's less a cosmic accident than a reflection of the universe's natural rhythm. When scientists talk about emptiness, they mean it quantitatively. Fewer atoms per cubic meter, less dark matter, lower gravitational potential. But even in the most underdense regions, space is never truly empty. There are still particles, stray atoms, the faint hiss of the cosmic microwave background, and perhaps a handful of galaxies wandering through the dark. Some of those galaxies, like lonely lanterns, form small groups bound by their own gravity. They still birth stars, they still evolve, they still shine. The void is not a dead zone, it's a quieter part of the symphony. Thinking about this can make your mind drift in strange directions. What does it mean to live in a region defined by what it lacks? We're used to thinking of ourselves as inhabitants of a galaxy, a planet, a solar system, all things. But here we are, possibly centred in a great absence. It's almost poetic, though not in the way of metaphor or mystery, more in the simple fact that our address in the universe includes a kind of emptiness. If someone asked where we are, we could say the Milky Way, the local group, and then the KBC Void. It's like saying you live in a small town in a wide plain surrounded by open air. Astronomers estimate the KBC Void's diameter at roughly 1 billion light-years, give or take a few hundred million. That's enormous, yet it's not unique. Other voids have been mapped elsewhere in the cosmos. The Butter's Void, the Eridanus Void, the Dipole Repeller, each with its own strange dimensions. What makes the KBC Void intriguing is that we might be inside it, looking outward from the middle rather than observing from the edge. That vantage point changes everything. When you stand in the middle of emptiness, distances appear different. Light travels through less matter. Gravitational lenses shift slightly, and expansion looks faster. To correct for that, astronomers need to model both the emptiness and the thin web of galaxies that thread through it. Even the process of mapping such a region requires immense patience. The light from the galaxies used to measure it has travelled for hundreds of millions of years. By the time it reaches our telescopes, it carries the history of expansion, the imprint of dark energy, and the subtle pull of nearby clusters. Computers then process that information, building a virtual map of density. Where the density drops, you have a void. Where it rises, you have a filament. It's like using the ripples on a pond to reconstruct the stones that caused them. Each observation is a tiny clue, a hint that somewhere out there space is thinner, quieter, different. If you think about it long enough, it becomes hard to separate yourself from the scale of it. The idea that the Milky Way could sit inside a bubble a billion light-years wide makes everything we know feel very local. Our solar system, which once seemed vast enough to define adventure, becomes a speck inside a speck, surrounded by a delicate void that most of us will never feel, but which shapes our view of everything. There's something serene about that, something that puts even the busiest human moments into a kind of perspective. And yet, this isn't a story of insignificance. The KBC Void isn't a sign that we're lost or hidden in the cosmos. It's a reminder that even the quietest corners of the universe are part of the larger pattern. The void exists because of gravity and time, the same forces that built galaxies and stars. The emptiness is sculpted by presence. The galaxies around its edges pull gently outward, leaving the centre thinner. Over billions of years, these processes create the web we see today. The universe breathes in structure, then exhales into stillness. We just happen to be somewhere between the two. Astronomers continue to refine their measurements, using new surveys and instruments to test whether the KBC Void is real, how deep it runs, and what it means for cosmology. Some findings suggest the void might not be as empty as first thought. Others hint that it could be even larger. But whatever the final numbers, the concept has already changed how we think about our cosmic address. We're not just part of a galaxy. We're part of a structure of density and absence, brightness and darkness, matter and space. The universe, in all its vastness, is a balance of these opposites, and the KBC Void is one of its quieter harmonies. It's strange to realise that the emptiness surrounding us could influence so much, from how light travels to how fast the universe seems to expand. The nothing between galaxies isn't passive. It shapes the cosmos as surely as the galaxies themselves. That's one of the quiet truths hidden in this story. The space between things matters. The silence between notes defines the music. The empty parts of the universe define the shape of everything we see. And so, as you listen now, somewhere in that silence a thought lingers. The Milky Way drifts in an invisible bubble. Light passes through it, stretching a little more freely, slowing a little less. Galaxies beyond its edge shimmer faintly as their light bends through the thinness. From our small point in that immense calm, we build telescopes, gather data, and slowly, gently, try to measure the size of the emptiness we inhabit. When you look up at the night sky, what you see feels endless. Thousands of stars scattered across the blackness, their light carrying the memory of ancient fires. But what lies between those points of light is where the real mystery begins. That dark canvas, which looks like nothing at all, is not a simple void. It's structured, layered, and filled with the faint echoes of creation. The deeper scientists have looked into the spaces between galaxies, the more they've realised that those stretches of apparent nothingness are as complex and dynamic as the stars themselves. To understand the KBC Void, or any cosmic void, you first have to understand what fills the universe when it appears empty. At first glance, the idea seems contradictory. How can something called a void be filled with anything? The answer comes down to scale. On human terms, space is unimaginably vast. The nearest star to us, Proxima Centauri, is over 4 light-years away, and even that tiny number represents a distance so huge that it's almost meaningless in everyday language. But when astronomers talk about cosmic voids, they're thinking millions of times larger than that. A void might stretch hundreds of millions of light years across, and within that enormous expanse matter isn't completely absent, it's just very thinly spread. A few atoms per cubic metre, faint traces of hydrogen gas, and the occasional lonely galaxy drifting through the dark. To picture what that means, it helps to imagine an ocean. Not a calm blue one, but an invisible sea made of galaxies and gas. In some regions, the water is dense and swirling, forming massive clusters and superclusters. In others, it thins out almost entirely, forming vast translucent basins. Those basins are the voids. They aren't static. Over billions of years, they've been shaped by gravity, by expansion, and by the gentle tug-of-war between dark matter and dark energy. If you could somehow stand at the edge of one and look across it, you wouldn't see a perfect sphere of blackness. You'd see faint glimmers of distant galaxies curving away at the boundaries, the bright filaments of the cosmic web arching over a deep, dim hollow. The idea that the universe is built from both fullness and emptiness wasn't obvious at first. For a long time, astronomers thought galaxies were sprinkled evenly through space. But in the 1980s, with the first large-scale surveys, they started to realise that galaxies tend to gather in enormous sheets and strings, leaving immense gaps in between. The discovery of the Butter's Void in 1981 shocked scientists. It was a region nearly 330 million light-years across that contained only a few dozen galaxies, a vast emptiness surrounded by a thin shell of matter. That was the first clue that the universe isn't uniform, but rather shaped like a sponge, full of holes. Since then, astronomers have mapped thousands of such voids, finding that they make up most of the universe's volume. The cosmic web, as it's now called, is an intricate pattern of filaments and clusters, with the voids occupying the spaces between them. In fact, if you could shrink the entire observable universe to the size of a sphere you could hold in your hand, most of what you'd be holding would be empty. The galaxies, clusters, and dark matter filaments would be thin wisps like cobwebs frozen in motion, tracing the edges of enormous gaps. These gaps are not just the leftovers of creation, they're part of how the universe grows. In the early universe, matter was almost evenly distributed, with tiny fluctuations, slightly denser patches where gravity could begin pulling material together. Over time, those dense regions became the seeds of galaxies and clusters. As they drew in more matter, the spaces between them grew emptier. The rich got richer, and the poor grew poorer, cosmically speaking. Gravity is the sculptor, and emptiness is the result. The voids expand as the dense regions collapse, each reinforcing the other's evolution. That's how the universe came to have its current structure, a foam of galaxies with nothingness in between. The KBC Void, if it exists as described, would be one of the largest of these structures, surrounding our own galaxy and stretching outward for about 1 billion light-years. To find evidence for something like that, scientists study the distribution of galaxies in every direction. They measure how bright they are, how far they've travelled, and how much their light has been stretched by the expansion of space. By comparing those observations with computer simulations of the universe, they can infer where the empty regions must be. The light of galaxies serves as a tracer, outlining the cosmic web like lanterns revealing the walls of an invisible cavern. Inside a void, galaxies are rarer, and those that do exist tend to be small and faint. They form stars more slowly, and they evolve differently from their cousins in dense clusters. That's because there's less gas to feed star formation and fewer gravitational interactions to stir things up. The result is a calmer environment, not completely still, but gentler, quieter. Even on a galactic scale, emptiness changes behaviour. Some astronomers call these isolated systems void galaxies, and they offer valuable clues about what it means to live in cosmic solitude. One example is the galaxy known as MCG +01 02 015, often referred to simply as the Void Galaxy. It sits almost alone in a vast region of space with no nearby neighbours for tens of millions of light-years. observations show that it's forming stars at a modest rate, surrounded by faint gas that may once have been part of a larger structure. Its isolation has preserved it from the chaos of galactic collisions that shape more crowded regions. It drifts quietly, evolving on its own schedule, like a candle burning in the middle of an empty room. When you think about it, that kind of isolation has parallels with our own place in the KBC Void. The Milky Way isn't lonely in a literal sense. We have nearby companions like the Andromeda Galaxy and the Magellanic Clouds. But on the scale of hundreds of millions of light-years, our region may still be underdense. The galaxies around us could be slightly farther apart, the cosmic wall slightly farther away. That difference might be almost invisible from a human perspective, but it matters when you're measuring the expansion of the entire universe. One of the elegant aspects of cosmology is how much information can be extracted from such tiny details. The faintest changes in the brightness or redshift of galaxies can reveal the shape of structures too vast to comprehend directly. To detect a void, astronomers don't look for darkness, but for subtle patterns of spacing. They chart how galaxies cluster together and where they do not. The maps that emerge are astonishing. Three-dimensional webs where each point of light marks a galaxy, and the empty spaces between them reveal the shape of the voids. These maps are built from enormous datasets, gathered by telescopes like the Sloan Digital Sky Survey, which has catalogued millions of galaxies over the past 2 decades. The picture that's emerging from this data is one of a universe that's far more intricate than anyone imagined. It isn't random, but it isn't neatly ordered either. It's a complex network of connections and absences, a pattern shaped by physics and time. And in that network, the voids are not mistakes or gaps to be ignored. They're vital components of the whole. They influence how galaxies move, how light travels, and even how the cosmic expansion appears to us. The universe doesn't just grow in the crowded places, it grows in the empty ones too. What's especially striking about this structure is how universal it is. No matter where astronomers look, they find the same pattern repeating. Filaments, clusters, voids. The scale changes, the density changes, but the architecture remains consistent. It's fractal-like, though not perfectly so. The same principles that shape a small void between local galaxy groups can also shape the enormous hollows that stretch across billions of light-years. That consistency suggests that the universe has been governed by the same simple rules since its earliest moments. Gravity pulling matter together, expansion stretching space apart, and dark energy pushing at the edges. The balance between these forces determines how the cosmic web evolves. Gravity tries to gather everything, to clump matter into stars and galaxies. Dark energy, a mysterious pressure that pervades space, does the opposite. It accelerates the expansion of the universe, pulling everything apart. The voids are where dark energy wins, where expansion outpaces gravity's pull. They're the growing bubbles in the cosmic foam, expanding faster than the dense regions around them. Over time, these bubbles merge, creating larger and larger empty spaces. The KBC Void could be one of the results of that process, a mature bubble still stretching quietly beneath the galaxy's glow. Even though we call them empty, voids are far from featureless. They contain faint wisps of gas, filaments of dark matter, and occasional clusters that act as islands in the emptiness. In simulations, these structures appear as delicate threads stretching across the hollows like cobwebs floating in darkness. Light from distant galaxies passes through them, bending slightly under their weak gravitational influence. This lensing effect, though minute, can be measured, offering another way to study the shape of the voids. The study of these regions has become a thriving field in modern cosmology. Scientists use them to test ideas about dark energy, cosmic inflation, and the overall geometry of the universe. Because voids are sensitive to the underlying physics of expansion, they serve as natural laboratories for probing the nature of space itself. Some researchers even suggest that studying how galaxies move inside voids could reveal clues about modified gravity, theories that go beyond Einstein's general relativity. The emptiness, it turns out, is full of information. To understand why voids are so significant, consider how light behaves as it moves through space. When light travels through a dense region, gravity slows it slightly, bending its path. When it passes through a void, it does the opposite. The lack of matter allows it to stretch and speed up. These tiny variations accumulate over billions of years, altering the apparent brightness and position of distant galaxies. By analysing those distortions, astronomers can reconstruct the invisible landscape of density that light has crossed. It's a bit like studying the ripples on the surface of a pond to understand the shape of the stones beneath. The fact that light carries this information makes it one of the most valuable tools in cosmic cartography. Every photon that reaches our telescopes has travelled through countless regions of differing density, each leaving its fingerprint on the light's journey. When scientists analyse that light, they're effectively reading a story written across the universe, a record of where the matter is and where it isn't. Through that process, the structure of the voids, including our own, becomes clearer, and so, beneath the stars, beyond the glittering constellations we recognise from Earth, lies a vast network of invisible shapes. We are surrounded by emptiness that is not truly empty, structured by the slow dance of gravity and expansion. The KBC Void is just one part of that immense pattern, one hollow in a cosmic web that stretches as far as our instruments can see. It's strange to think that we might live inside such a space, but it's also perfectly natural. The universe has been carving these hollows since its earliest days. From the outside, a void might seem lifeless, but when you look closely, it's filled with motion. Galaxies drift through it. Light crosses it. Space itself expands within it. The quiet between galaxies is not a pause in the universe's activity. It's part of its breathing. Each empty region allows the denser regions to exist, and vice versa. The stars we see tonight are suspended within that balance. When astronomers began to map the positions of galaxies across the sky, they expected to find a fairly even scattering, as if the universe had been dusted with stars at random. Instead, what emerged from the data looked almost biological. Galaxies were not isolated dots, but parts of long chains, great arcs, and dense nodes, all connected by invisible bridges of matter. Between those bright strands stretched enormous empty spaces so vast that they dwarfed everything else. This discovery, which became clear through decades of observation and data from massive sky surveys, revealed one of the universe's most striking features. It's not a uniform ocean of galaxies, but a web. A cosmic web made of threads and holes, filaments and voids, stretching across billions of light years. This network forms the largest structure known to science. Each thread of the web is a filament containing clusters and superclusters of galaxies, bound together by gravity and dark matter. The points where those threads intersect are home to the densest gatherings, cosmic crossroads where thousands of galaxies reside in tight proximity, and the spaces between them, the holes in the pattern, are the voids, the nearly empty bubbles that make up most of the universe's volume. Taken together, the whole arrangement resembles the structure of a sponge or the texture of foam frozen in motion. It's an architecture that seems chaotic at first glance, but follows clear physical rules, shaped by the pull of gravity, the push of cosmic expansion, and the faint ripples left over from the earliest moments after the Big Bang. To understand how this web came to be, you have to look back nearly 14 billion years to the time when the universe was young, hot, and nearly uniform. After the Big Bang, matter was spread almost evenly throughout space, with only minute variations, tiny ripples in density, 1 part in 100,000. These faint fluctuations, recorded in the cosmic microwave background radiation, were the seeds of all future structure. Where the density was slightly higher, gravity pulled in more matter, amplifying the difference. Over billions of years, those small overdense regions became galaxies, clusters, and the filaments connecting them. The underdense regions became voids. It's a process called hierarchical structure formation, and it's the reason why the universe today looks like an immense web instead of a smooth fog of stars. Dark matter played a crucial role in this evolution. Unlike ordinary matter, which interacts with light and can form atoms, dark matter only interacts through gravity. It doesn't glow, it doesn't absorb radiation, but its mass shapes everything. Computer simulations show that dark matter formed the scaffolding of the cosmic web. As the universe expanded and cooled, ordinary matter, hydrogen, helium, and traces of heavier elements fell into the gravitational wells carved by dark matter. Stars ignited, galaxies formed, and the visible universe took shape along that invisible framework. If you could somehow remove all the normal matter and leave only dark matter, the pattern would look almost identical to what we see in galaxy surveys. The luminous structures we observe are just the bright frosting on an unseen cake of dark mass. These simulations are not abstract pictures. They're based on physics, on equations that describe gravity, fluid dynamics, and expansion. They use billions of virtual particles to represent dark matter and gas, letting researchers watch how the cosmic web grows over time. One of the most famous is the Millennium simulation, which modelled a cube of the universe more than 2 billion light-years wide. When the results were visualised, the outcome was mesmerising. A glowing network of filaments stretching in all directions, punctuated by knots of dense clusters and surrounded by vast, dark voids. The resemblance to the real universe mapped through telescopes was uncanny. It confirmed that the same basic laws governing a single galaxy also govern the largest structures known. Gravity, simple and universal, is enough to weave the cosmic web. Within this immense structure, galaxies move like beads sliding along threads. Their motion is influenced by both the attraction of nearby clusters and the expansion of space itself. Over cosmic time, filaments draw material from the surrounding voids, feeding galaxies and fueling star formation. The voids, in turn, expand, growing emptier as matter flows away. This ongoing exchange gives the universe its dynamic texture. Dense regions becoming denser, empty regions stretching further. Even now, billions of years after the first galaxies formed, the web is still evolving. It's not static. It's a living, shifting lattice of gravity and time. When scientists chart the positions of galaxies from our own vantage point, the picture that emerges is breathtaking. The Sloan Digital Sky Survey, one of the most ambitious mapping projects ever undertaken, has plotted millions of galaxies across more than a third of the sky. When viewed in 3 dimensions, these galaxies form a structure that could easily be mistaken for neurons in a brain or filaments in living tissue. The comparison isn't just poetic, it's rooted in mathematics. Both systems show similar scaling behaviour, with patterns repeating at different sizes. The cosmic web is not alive, but it shares the geometry of complex networks found throughout nature. Our own place in this grand design lies within one of the web's thinner filaments, inside a region that might itself be surrounded by a large void, the KBC Void. From this position, we look outward and see the walls of denser clusters at the edges of the bubble. Light from those distant galaxies passes through the underdense region we inhabit, subtly stretched by the lower gravitational pull. That stretching can make the universe's expansion appear faster locally than it does when measured across denser regions. This is one reason the KBC Void has become so important in modern cosmology. It could offer a natural explanation for why some measurements of the Hubble constant disagree with others. The structure of the cosmic web also explains why galaxies tend to cluster in familiar patterns. Groups like our local group, which includes the Milky Way, Andromeda, and about 50 smaller galaxies, are not isolated objects floating randomly. They're knots in the filament. Those filaments connect to larger structures like the Virgo supercluster, which itself is part of an even grander arrangement known as the Laniakea supercluster. Laniakea spans over 500 million light-years and contains around 100,000 galaxies. Its boundaries are defined not by walls or edges, but by the flow of galaxies towards shared gravitational centres. The cosmic web is hierarchical, each level connected to a larger one, each filament feeding into a broader network. The density variations that define this web are subtle but crucial. Where the density is slightly above average, galaxies form faster, merging and interacting frequently. In low-density regions like voids, galaxies evolve in relative isolation. This creates a kind of natural laboratory. By comparing galaxies in dense filaments with those in voids, astronomers can study how environment affects cosmic evolution. For instance, galaxies and clusters often have less cold gas and lower rates of star formation, likely because interactions and gravitational stripping remove their resources. In voids, galaxies are more pristine, their gas reservoirs intact, their evolution slower. The universe, in that sense, experiments with different conditions across its own landscape. Dark energy, the mysterious force driving the acceleration of cosmic expansion, also interacts with this structure in subtle ways. In the densest regions, gravity resists expansion, slowing it slightly. In the emptier regions, there's less mass to counteract dark energy, so expansion accelerates. This means the cosmic web doesn't just expand uniformly. The voids expand faster, stretching the filaments and making the web appear to thin out over time. The result is a dynamic equilibrium where matter keeps clustering, even as the overall fabric of space stretches. Eventually, if dark energy continues to dominate, the filaments may drift farther apart, leaving the web more diffuse, though never completely disconnected. Observations from new instruments like the Dark Energy Spectroscopic Instrument and the Euclid Space Telescope are refining this picture, mapping the cosmic web with unprecedented accuracy. They're revealing not only where galaxies are, but how they move. These velocity maps show streams of matter flowing from the voids toward the filaments, tracing the gravitational currents that shape the universe. It's as if space itself has weather patterns. Slow winds of matter drifting through invisible valleys, gathering in bright knots. Over time, these flows smooth out irregularities, reinforcing the network's overall structure. The idea that the universe looks like a web also changes how we think about scale. On Earth, distance feels absolute. A kilometre is always a kilometre. In the cosmic web, distance depends on expansion. The filaments are moving apart, their separations increasing as the universe grows. When we look at a galaxy billions of light-years away, we're seeing it not as it is now, but as it was when light left it, sometimes before our own solar system formed. The web we see is a fossil, a frozen image of a living system that continues to evolve. Every observation is a look backward in time, and every point of light is a record of the web's ongoing creation. It's remarkable that something so immense can be described by relatively simple principles. The cosmic web's shape emerges naturally from gravity acting on an expanding medium. The details are complex, but the foundation is straightforward. Where there's slightly more matter, gravity amplifies it. Where there's slightly less, expansion dominates. Over billions of years, those tiny imbalances sculpt the pattern we see today. It's a self-organizing process, one that doesn't require fine-tuning or external design. The universe builds its own architecture through the quiet interaction of its most basic ingredients. For us, living within this structure means that everything we observe, every galaxy, every supernova, every measurement of cosmic expansion, is influenced by our position inside the web. When we point a telescope outward, the light we gather has travelled along those threads, through the surrounding voids, across the subtle curvature of space. The cosmic web isn't just a distant backdrop, it's the context of our existence. The Milky Way is one node in an immense network, connected by filaments of gravity to countless others. Our place in that pattern shapes not only how we see the universe, but how the universe evolves around us. In this interconnected structure, emptiness and fullness define each other. Without the voids, the filaments wouldn't stand out. Without the filaments, the voids would have no shape. They're complementary aspects of a single whole. The KBC Void, if confirmed, would simply be one of the countless hollows in this grand lattice, a space that reminds us how deeply the universe depends on both presence and absence. Every bright galaxy we see is framed by invisible space, and every stretch of darkness holds the memory of light that once passed through it. The more astronomers learn about the cosmic web, the more it becomes clear that the universe isn't just expanding, it's evolving in texture. The patterns of matter and void are the fingerprints of time itself, imprinted across billions of light years. To study them is to read the universe's diary, written not in words but in density, motion and light. When scientists first began to map the nearby universe in detail, they weren't expecting to find anything particularly unusual about our own cosmic neighbourhood. The Milky Way, after all, seemed to occupy a fairly ordinary region of space, surrounded by galaxies much like our own. Yet as surveys became more sophisticated and data sets grew larger, small hints began to appear that something about our corner of the cosmos didn't quite match the averages. The light from distant galaxies seemed to behave just a little differently than predicted, and the distribution of matter within a few 100 million light-years of Earth appeared subtly thinner than it should have been. Out of this accumulation of quiet anomalies came a surprising hypothesis, that our galaxy might sit near the centre of a vast underdense region, a bubble within the larger cosmic web. This idea eventually came to be known as the KBC Void, named for the three astronomers who first described it in detail: Ryan Keenan, Amy Barger, and Lennox Cowie. The story begins with data, as most modern cosmological discoveries do. In the early 2000s, multiple sky surveys were cataloguing the brightness, colour and distance of tens of thousands of galaxies across the observable universe. One of the key tools in this effort was the concept of redshift, the stretching of light waves as galaxies move away due to the expansion of space. The higher the redshift, the farther and faster the galaxy. By compiling redshift data from a range of distances, astronomers can build a three-dimensional map of the local universe, showing where galaxies cluster and where space appears comparatively empty. When Keenan, Barger, and Cowie analysed these distributions, they noticed a trend that didn't quite fit the expected uniformity. At distances out to roughly 300 million light-years, the density of galaxies seemed lower than average. Beyond that range, the density began to rise again, approaching what cosmologists considered typical for the universe as a whole. The pattern suggested that we might be inside a large region where the number of galaxies per volume was suppressed, a kind of cosmic basin surrounded by denser walls farther out. This wasn't the first time anyone had suggested that possibility, but the team's analysis was among the most comprehensive. They combined data from multiple independent surveys, cross-checked their measurements against known galaxy clusters, and concluded that the effect was real enough to merit serious consideration. In 2013, they published their results in the Astrophysical Journal, describing what they called a local underdensity. The estimated diameter of this region was about 1 billion light-years, enormous by any standard, and its centre appeared to coincide roughly with our position in the Milky Way. Within it, the density of galaxies and matter was roughly 20 to 30% lower than the cosmic mean. To visualise this, imagine a sphere so large that it contains thousands of superclusters, yet overall it's missing a significant fraction of the matter one would expect. That is the scale of the KBC Void. The idea raised immediate interest and a fair amount of scepticism. On one hand, cosmic voids are a normal part of the large-scale structure of the universe. They occupy most of its volume, separated by filaments and clusters of galaxies. But on the other hand, finding ourselves near the centre of one would be unusual, statistically speaking. Cosmologists have long operated under what's known as the Copernican principle, the notion that Earth, and by extension humanity, doesn't occupy a special or privileged position in the cosmos. If we happen to live inside an unusually large void, some argued, wouldn't that violate this principle? Others countered that the principle is about probability, not impossibility. Someone has to live somewhere, and a small fraction of observers would naturally find themselves in underdense regions. The scientific intrigue around the KBC Void grew because of its potential connection to another puzzle, the disagreement over how fast the universe is expanding. Measurements based on the early universe, using the cosmic microwave background radiation, yield a Hubble constant of about 67 km per second per megaparsec. Measurements based on the local universe, using supernovae and Cepheid variables, suggest a higher value, around 73. The difference between these numbers, though small, has persisted even as observational precision improved. If our galaxy resides in a region of lower density, the local rate of expansion would be slightly faster due to reduced gravitational slowing. That could make nearby galaxies appear to recede more quickly than the cosmic average, mimicking a higher Hubble constant. The KBC Void, therefore, offered a potential explanation for at least part of the so-called Hubble tension. To test this, scientists began constructing detailed models of the local universe, incorporating both visible galaxies and inferred dark matter. Using data from surveys like the 2-micron All-Sky Survey, 2MASS, and the Sloan Digital Sky Survey, SDSS, they simulated how light would travel through a large underdensity and how that would influence observed redshifts. The results showed that a void of the size and depth proposed by Keenan and his colleagues could indeed account for a modest increase in the apparent local expansion rate. Though not enough to resolve the entire discrepancy, still, the alignment between theory and observation was striking enough to keep the hypothesis alive. The difficulty in confirming such a structure lies in the nature of cosmic mapping itself. The universe is vast, and our observations are limited by both distance and perspective. We can only observe from one point within the structure we're trying to measure. That means astronomers must infer the three-dimensional shape of the void from the distribution of galaxies and their motions, all projected onto the sky from our position near the centre. It's like trying to deduce the shape of a room by shining a flashlight around from a single spot inside it. The patterns of brightness and shadow tell you something about the walls, but not everything. Over the following years, several independent studies examined the same region using different data sets. Some found evidence consistent with the KBC Void, while others suggested that the local underdensity might be smaller or less pronounced than originally proposed. A 2019 study using data from the Cosmic Flows 3 catalogue found that our local region does appear to be underdense by roughly 10 to 20%, but perhaps not enough to classify it as a true void on the scale of 1 billion light-years. Even so, the overall trend, that our local neighbourhood is slightly emptier than average, remained consistent. One of the key ways astronomers refine these measurements is by studying the peculiar velocities of galaxies, that is, their motions relative to the smooth expansion of space. In an ideal uniform universe, galaxies would move away from each other at speeds proportional to their distance, following the simple rule of Hubble's law. But in reality, gravity causes deviations. Galaxies near massive clusters move slightly faster or slower depending on the surrounding density. By analysing these deviations, scientists can infer where matter is more or less concentrated. In regions of low density like a void, galaxies tend to flow outward, pulled by the stronger gravity of the surrounding walls. When researchers modelled these flows near our position, they found patterns that fit with the presence of a large underdensity. The name KBC Void became shorthand for this entire concept. Not just a specific hole, but the idea that our local cosmic environment might be part of a larger underdense region influencing our observations. Its edges, if they exist, would be marked by denser clusters of galaxies such as the Perseus-Pisces supercluster and the Coma Wall. Beyond those, the universe returns to its average density. Inside the boundary, everything from the motion of galaxies to the propagation of light bears the subtle imprint of that thinness. Despite the excitement, No one claims that the KBC Void is an absolute fact. It's still a hypothesis under examination. The data supporting it are strong but not definitive, and the structure itself may not have a clear boundary. Voids in the universe are rarely perfect spheres. They're irregular, overlapping and constantly evolving. What Keenan, Barger and Cowie identified might be part of a network of connected underdensities, rather than a single isolated bubble. In that sense, our galaxy could lie in a transitional zone, not in the deepest heart of a void, but within a broad, underdense corridor linking multiple hollows of the cosmic web. Nevertheless, the discovery was an important reminder that our understanding of the universe is always filtered through our position within it. We observe the cosmos from one vantage point, inside a galaxy, inside a cluster, inside a structure whose boundaries we can only infer. The KBC Void highlights how much those boundaries matter. A small difference in local density can change our interpretation of cosmological measurements, just as a shift in elevation changes the horizon we see. The idea also carries philosophical weight. For centuries, humans have struggled with the question of our cosmic significance. Each scientific revolution, the heliocentric model, the discovery of galaxies, the realization of an expanding universe, has seemed to push us further from the centre. And yet, if the KBC Void exists, we may once again find ourselves near the middle of something, even if that something is an emptiness. It's not a return to the old idea of centrality, but a reminder that the universe's structure can place us in unique positions without conferring special importance. The view from here is just one among countless possible vantage points scattered across the cosmic web. As new instruments come online, especially those capable of mapping galaxies at greater distances and with finer detail, the picture will sharpen. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, for example, will chart billions of galaxies over the next decade, potentially revealing the full extent of local structures like the KBC Void. Combined with data from radio surveys and gravitational lensing measurements, these observations could confirm whether our region truly is as underdense as current models suggest. Even if the final answer turns out to be more nuanced, perhaps a patchwork of smaller voids and filaments rather than one vast bubble, the effort to map it is valuable. It deepens our understanding of how the universe's large-scale structure influences what we see. It teaches us that emptiness, as much as matter, has shape and consequence. Every photon that reaches our telescopes has crossed that structure, its path subtly curved and its energy slightly altered by the density of space it passed through. The work of Keenan, Barger and Cowie opened a door to a different way of thinking about our place in the cosmos. Instead of imagining ourselves as detached observers looking out at a uniform expanse, we begin to see ourselves as participants in a dynamic environment shaped by vast flows of matter and energy. Our corner of the universe may be quieter, thinner, more open than others, but it is part of the same grand pattern that links everything together. Trying to measure a void in the universe sounds almost like a riddle. How can anyone hope to quantify something defined by its lack of contents? Yet that's exactly what astronomers do when they study the structure of the cosmos. They measure nothing, or more precisely, they measure how much less of something there is. The story of how scientists detect, map, and analyse the great underdensities of the universe, such as the KBC Void, is a study in precision, patience, and inference. Every method relies on the same principle. If you can't see what's missing directly, you can study what remains and work backward. In astronomy, you rarely get to handle your subject matter. You can't fly to a distant galaxy or scoop up a handful of intergalactic space for testing. Everything we know comes from light. Light, in all its forms, from visible waves to radio signals to X-rays, is the courier of cosmic information. It carries clues about where matter lies, how it moves, and how space itself behaves. When astronomers talk about mapping the universe, they're really describing a kind of grand detective work. analysing the patterns in this light to infer the unseen architecture of space. The first step in measuring nothing is counting something. Galaxies are the visible traces of the large-scale structure of the universe. If you count enough of them across a wide enough region, you begin to see where they gather and where they thin out. In practice, this means using powerful telescopes equipped with sensitive detectors to record millions of galaxies over vast portions of the sky. Surveys like the Sloan Digital Sky Survey, the 2-micron All-Sky Survey, and more recently the Dark Energy Survey have catalogued the positions, brightness and redshifts of galaxies across billions of light-years. From this data, astronomers build 3-dimensional maps showing how galaxies populate space. In a perfectly uniform universe, those maps would reveal a smooth distribution, galaxies evenly scattered in all directions. But the real universe is far from uniform. The maps instead show enormous clusters where galaxies pack tightly together, long filaments connecting those clusters, and between them, the voids. Vast, dark regions where the number of galaxies drops sharply. The contrast between these regions is what defines the web-like pattern of cosmic structure. By quantifying the density of galaxies in each volume of space, astronomers can calculate how underdense or overdense a region is compared to the cosmic average. To identify a void, scientists often use algorithms that search for contiguous regions of low galaxy density. One common method involves dividing the sky into cubes or cells, and counting how many galaxies fall within each one. If a large group of adjacent cells shows fewer galaxies than expected, it might mark the presence of a void. The exact thresholds vary depending on the survey and the scale of interest. Some voids are small, spanning only tens of millions of light-years. Others, like the one proposed around our galaxy, stretch hundreds of millions or even a billion light-years across. The larger the void, the more subtle its signature, because small differences in density are spread over enormous distances. But galaxies alone don't tell the full story. Much of the universe's mass is invisible, made of dark matter that doesn't emit or absorb light. To detect its presence, astronomers rely on gravity. One of the most powerful techniques is gravitational lensing, the bending of light by massive objects. When light from a distant galaxy passes through a region filled with matter, its path curves slightly, just as light bends when it passes through glass. By measuring the degree of distortion in the images of background galaxies, astronomers can map the distribution of mass, including the unseen dark matter. In regions where light bends less than expected, it suggests an underdensity, a void. Gravitational lensing studies are delicate work. The effect is tiny, often less than 1 part in 1,000 of the galaxy's apparent shape. But when averaged over millions of galaxies, the signal becomes clear. Observations from instruments like the Subaru telescope and the European Space Agency's Euclid mission are providing increasingly detailed maps of these lensing signals, revealing how dark matter threads through space and where it thins out. These measurements help confirm that voids are not empty bubbles, but gently sloping valleys in the gravitational landscape of the universe. Another method relies on the cosmic microwave background, CMB, the afterglow of the Big Bang. This radiation, which fills all of space, is remarkably uniform, but it isn't perfectly smooth. As it travels through the universe, the CMB interacts with the large-scale structure, including voids and clusters. When photons from the CMB pass through a massive cluster, they gain a tiny bit of energy from the gravitational field, a process known as the Sachs-Wolf effect. When they pass through a void, they lose a bit of energy. By analysing these small temperature fluctuations, scientists can infer where large voids exist along the line of sight. The technique is subtle, the changes are only a few millionths of a degree, but it offers another independent way to detect underdense regions. Redshift surveys provide yet another line of evidence. Because the universe is expanding, galaxies farther away move faster, stretching their light toward the red end of the spectrum. The amount of redshift tells us how far a galaxy's light has travelled and how long ago it left. but the expansion isn't perfectly uniform. Local gravitational effects add small variations to the observed redshift. Galaxies inside a void, for example, experience less gravitational pull from their surroundings, so they tend to move outwards slightly faster. This creates a characteristic pattern in the redshift data, a kind of outward flow that reveals the void's presence. To measure this effect, astronomers model the velocity field of galaxies, the directions and speeds of their motions relative to the overall expansion. They look for regions where the flow diverges, where galaxies are moving away from a central zone faster than the average expansion would predict. These divergent flows are the fingerprints of voids. When researchers applied this technique to our local region, they found signs of outward motion consistent with an underdensity roughly matching the dimensions of the KBC Void. Of course, measuring nothing comes with complications. Every observation carries uncertainties, and distinguishing a genuine underdensity from random statistical noise requires careful analysis. The universe's structure isn't perfectly regular, and small fluctuations can mimic void-like patterns. To confirm a void's existence, astronomers cross-check multiple lines of evidence: galaxy counts, gravitational lensing, peculiar velocities, and CMB distortions. Only when all these indicators align can they confidently declare that a region is truly underdense. One of the more philosophical challenges in measuring voids is that they don't have sharp boundaries. A cluster of galaxies has a clear edge, defined by the limits of its gravitational binding. A void, by contrast, fades gradually into surrounding space. Its edge is defined statistically, not physically, the point where the density returns to the cosmic mean. In this sense, voids are more like gradients than objects. They're defined not by what they contain, but by how their properties change relative to their surroundings. When scientists describe the KBC Void as 1 billion light-years wide, they're referring to the region over which the density remains below a certain threshold, not a solid shell enclosing emptiness. Despite their intangible nature, voids have measurable effects. Light travelling through them is slightly altered, both in brightness and in timing. The absence of mass means there's less gravitational slowing, so photons move through voids a little more freely. This subtle effect can shift the apparent brightness of distant supernovae, or change the timing of signals from cosmic background radiation. By analysing these shifts, scientists can indirectly estimate the depth and size of the voids. It's a form of negative measurement, detecting presence through absence, just as one might infer the shape of a missing puzzle piece from the pieces that remain. Computer simulations have become essential tools for refining these measurements. By generating virtual universes based on known physical laws, researchers can see how voids should appear in various models of cosmology. They can then compare those simulated patterns to real observations. When the two match, it's evidence that the model is close to describing reality. When they don't, it means something in the assumptions needs adjusting. Perhaps the nature of dark energy, the behaviour of dark matter, or the initial conditions of cosmic structure formation. Through these combined efforts, the once impossible task of measuring nothing has become a cornerstone of modern cosmology. Voids, far from being empty curiosities, are crucial to understanding how the universe expands and evolves. Their distribution, size and shape provide clues about the balance of forces shaping the cosmos. They help test theories of gravity and constrain the properties of dark energy. Even the way galaxies form and age depends on the environment created by these vast hollows. In a sense, studying the voids is like studying the universe's negative space, the background against which everything else gains definition. For the KBC Void, the process of measurement continues. Each new survey adds more detail, filling in the gaps in our local cosmic map. The goal isn't simply to confirm the void's existence, but to understand how it fits into the broader network of underdensities and filaments surrounding us. As data improves, the map of our region becomes more refined, revealing how the Milky Way sits amid this subtle gradient of density. Whether we're at the very centre of a great hollow or merely within one of its thinner regions, the act of measuring nothing continues to reshape our understanding of everything. It's humbling to realise that our knowledge of such vast emptiness comes down to counting tiny points of light and tracing their motions across billions of years. From those faint signals, astronomers reconstruct the invisible contours of space itself. Every measurement of nothing adds another thread to our picture of the universe, turning absence into information. The process demands an almost meditative patience, observing carefully, comparing quietly, letting patterns emerge from what at first appears to be void. And so, through the steady accumulation of light, numbers and models, we begin to chart the hollows that define the universe's shape. The act of measuring nothing turns out to be one of the most revealing ways of understanding everything. When you step outside on a clear night and look upward, you're gazing across a structure so immense that the human mind can barely contain it, and yet every part of that scene is local in a cosmic sense. The light you see with your eyes, from the stars, the faint band of the Milky Way, the occasional glimpse of another galaxy, all comes from a tiny fraction of the universe around us. The local universe, the region of space that includes the Milky Way and its immediate surroundings, is our neighbourhood in the cosmic web. It's not a single object or place, but a layered hierarchy of structures, each nested within the next, extending outward across hundreds of millions of light years. Understanding where we fit in this grand pattern is essential to understanding what it means to live inside the KBC Void, because the void's edges and depths are defined by the distribution of these nearby systems. Our home galaxy, the Milky Way, sits at the centre of a system known as the local group. This collection of galaxies stretches about 10 million light-years across, and includes more than 50 known members, though most of them are small and faint. The two most famous companions are the large and small Magellanic Clouds, visible from the southern hemisphere as glowing patches of light. The Andromeda Galaxy, roughly 2.5 million light-years away, is the largest member of the group, slightly bigger than the Milky Way, and the two galaxies are moving toward each other at about 100 kilometers per second. In a few billion years, they will merge to form a single larger system. Between these dominant galaxies, countless dwarf galaxies orbit, bound by gravity into a loose cluster of stars, gas, and dark matter. The local group is not isolated. It's part of a larger structure called the local sheet, a flattened region of space about 35 million light-years thick that contains several small groups of galaxies. This sheet acts like a gravitational plane, with galaxies lying roughly in the same cosmic layer. Above and below it, space becomes more sparsely populated. The sheet itself forms one strand of a broader filament that threads through the local universe, connecting to other clusters and superclusters. Beyond the local sheet lies the Virgo supercluster, the next major feature in our cosmic address. The Virgo supercluster spans roughly 110 million light-years and contains thousands of galaxies organised into numerous smaller groups. The Virgo cluster itself, a dense concentration of more than 1,000 galaxies located about 54 million light-years away, forms its gravitational heart. It's an immense structure, dominated by massive elliptical galaxies and clouds of hot gas visible in X-ray light. Our local group sits on the outskirts of this supercluster, drifting slowly toward its centre at several hundred kilometers per second. For much of the 20th century, astronomers believed the Virgo supercluster represented the largest coherent structure in our local universe. But as galaxy surveys expanded, it became clear that even this supercluster is just one part of a greater whole. In 2014, a team led by Brent Tully mapped the motions of more than 8,000 galaxies and discovered that the Virgo supercluster is only a small branch of an even larger structure, which they named Laniakea, Hawaiian for immense heaven. Laniakea spans about 500 million light-years and contains roughly 100,000 galaxies. It's defined not by strict boundaries, but by the flow of galaxies within it. every galaxy within Laniakea moves under the combined gravitational influence of the region's mass distribution, flowing toward a central area known as the Great Attractor, located in the direction of the constellation Centaurus. The Great Attractor is one of the most enigmatic regions of our local universe. It's a gravitational anomaly, an area where the mass concentration is so high that it draws galaxies from hundreds of millions of light-years around. Its core lies hidden behind the plane of the Milky Way, making it difficult to observe directly. But its influence is unmistakable. The motion of the Milky Way, the local group, and even the Virgo cluster all bear its signature. We are being pulled toward it, though the full nature of what lies there is still uncertain. Beyond the Great Attractor, at even greater distances, lies another massive structure known as the Shapley supercluster, a vast collection of galaxies that may mark the largest concentration of mass in the nearby universe. All of these components, the local group, the Virgo supercluster, Laniakea, the Great Attractor, and the Shapley concentration, form a complex network of matter extending hundreds of millions of light-years in every direction. When astronomers plot their positions, the result is a tangled web of filaments and walls surrounding enormous underdense regions. The KBC Void is believed to be one of these. It's as if we live in a sprawling city of galaxies, but our neighbourhood happens to be in one of the quieter suburbs, where the buildings thin out and open spaces widen. To understand how the local universe relates to the KBC Void, consider the balance between gravity and cosmic expansion. In regions filled with mass, clusters, filaments, and walls, gravity slows expansion slightly, pulling galaxies closer together. In regions where matter is sparse, like voids, there's less gravitational restraint, so expansion proceeds faster. The boundary between these zones isn't sharp, but gradual. As galaxies flow outward from voids into denser regions, they form a kind of cosmic circulation, a continuous exchange of motion that maintains the web structure. The local universe sits at the intersection of these flows, a place where gravitational attraction from clusters like Virgo and the Great Attractor competes with the outward push from surrounding emptiness. Mapping this flow of motion is one of the most challenging tasks in modern cosmology. To do it, astronomers use measurements of galaxy velocities relative to the overall expansion of the universe. They're peculiar velocities. By subtracting the general Hubble expansion, scientists can see how galaxies move due to local gravitational effects. When these peculiar velocities are plotted, they reveal a complex pattern, galaxies streaming toward clusters and away from voids. Our local group, for example, is moving at about 600 kilometers per second relative to the cosmic microwave background, a motion influenced by both nearby structures and the broader underdense environment. In recent years, high-precision maps of these motions have begun to reveal the outlines of the KBC Void itself. The flow of galaxies around our position suggests that we sit near the centre of a gently expanding region. The galaxies just beyond appear to be receding slightly faster than the cosmic average, consistent with a local underdensity. Meanwhile, those in the direction of denser regions, like the Perseus-Pisces supercluster and the Coma Wall, show the opposite behaviour, their motion slowed by gravity's pull. Together, these trends trace the boundary between the sparse interior of the void and the denser cosmic wall surrounding it. If we could view our local universe from afar, perhaps hundreds of millions of light-years above its plane, the scene would resemble a vast soap bubble, with our galaxy near the centre and luminous walls of galaxies curving around in every direction. These walls are not perfectly continuous, but patchy, made of clusters and filaments connected by faint bridges. The space inside the bubble would not be truly empty. A few isolated galaxies and wisps of gas would drift through it, shining faintly against the darkness. But compared to the dense filaments beyond, it would appear almost hollow. That's the environment we inhabit, a quiet basin in the great cosmic landscape. The scale of this basin is difficult to grasp. A billion light-years is roughly 10% of the observable universe's diameter. Within that space, light takes 1 billion years to travel from one side to the other. During that time, stars are born and die, galaxies merge, and the universe itself continues to expand. The fact that we can map such distances at all is a testament to the precision of modern astronomy. Every measurement of a galaxy's position, brightness, and velocity contributes a single data point to the immense three-dimensional mosaic that defines our local universe. Understanding this structure has practical consequences for cosmology. When scientists measure fundamental properties of the universe, such as its expansion rate or the density of dark energy, they rely on observations of nearby galaxies. If our local region happens to be underdense, those measurements can be biased. The KBC Void hypothesis reminds us that local conditions matter. Just as weather on Earth can vary from one region to another, while the planet's overall climate remains stable, cosmic conditions can vary from place to place within the larger universe. Recognizing those variations allows astronomers to correct for them and refine their models of cosmic evolution. The local universe also serves as a bridge between the human scale and the cosmic scale. It's large enough to reveal the grand architecture of the cosmos, but close enough for detailed study. Within a few 100 million light-years, astronomers can measure individual galaxies, track their motions, and even observe the gas and dark matter that shape them. These observations provide the context needed to interpret the deeper universe, where individual details blur into statistical patterns. The local universe is, in that sense, a cosmic laboratory, a region where we can study the interplay between matter, gravity, and emptiness up close. Our position within this network is both ordinary and unique. The Milky Way is an average galaxy, located in an average-sized group, drifting within a supercluster much like countless others. But the configuration of voids and filaments around us gives our region its own distinctive pattern. The KBC Void, if it exists as described, would make our neighbourhood slightly less crowded, slightly quieter, and slightly faster expanding than the cosmic average. That environment may influence subtle aspects of our observations, but it doesn't isolate us. Light, gravity, and cosmic expansion connect every part of the web, ensuring that no region is truly separate from the rest. When you step back and think about it, the term local universe is both comforting and humbling. It suggests proximity in a context where even the nearest objects are millions of light years away. Yet it also reminds us that, on cosmic scales, locality is relative. The structures that define our neighbourhood, the local group, the Virgo cluster, Laniakea and beyond, are merely the closest layers of a much larger pattern. They are the familiar streets of a city that stretches beyond sight, each illuminated by the faint glow of countless galaxies. From this vantage point, the idea of living in a cosmic void feels less strange. Our neighbourhood, though quiet, is still part of the vast network of existence. The space between galaxies, between clusters, even between superclusters, is what gives the universe its form. Without that space, without those underdense regions, there would be no contrast, no motion, no expansion. The local universe, with all its intricate connections and open gaps, is both our home and our window into the greater cosmos. If you could somehow step outside the Milky Way, past the haze of its spiral arms, beyond the local group and keep moving outward through the quiet expanses of the local universe, you would eventually begin to sense that the pattern of galaxies around you wasn't perfectly even. The farther you travelled, the more subtle the imbalance would become, a thinning here, a thickening there, until a picture began to form, the faint outline of a colossal hollow in the cosmic web. That hollow, spread across 1 billion light-years, is what astronomers call the KBC Void. But its shape is not the kind of neat geometry that a human imagination naturally conjures. There are no clean edges, no smooth walls, no well-defined borders. Instead, It's more like a shallow depression in a landscape that has never stopped changing. To understand its shape, you have to imagine something dynamic, elastic, and alive. A three-dimensional imprint of how matter and emptiness have wrestled for billions of years. When astronomers talk about the shape of a void, they mean the variation in density from one region to another, the contours of how matter thins and thickens across enormous distances. Mapping those contours is a challenge because the universe doesn't present them in sharp relief. Instead, they're hidden in the positions of galaxies and the speeds at which those galaxies move. If a cluster lies closer than expected, it means the space in between has expanded more quickly. If it lies farther away, the space there has expanded more slowly. When scientists plot those differences across all directions, the data begin to suggest a geometry, a vast, irregular cavity surrounded by denser filaments and clusters. The KBC Void, if represented this way, would appear as a faint underdensity centred roughly on our position in the Milky Way, gradually blending into the denser walls beyond. It's easy to imagine this void as a spherical bubble, because spheres are simple and intuitive, and in a rough sense that picture isn't entirely wrong. Many cosmological models assume spherical symmetry for simplicity, but in reality, voids are rarely perfect spheres. They're shaped by the same processes that form the filaments and clusters around them, and those processes are messy. Gravity tugs in all directions, the flow of matter is uneven, and dark energy pushes outward differently depending on local conditions. The result is that voids are lopsided, stretched, and interconnected. They merge with neighbouring hollows, forming chains of underdense regions that wind through the cosmic web. The KBC Void may not be a single, isolated bubble at all, but part of a larger network of connected emptiness stretching across the local universe. Computer simulations offer a way to visualize this structure. When researchers model the evolution of the universe using billions of particles of dark matter and gas, voids emerge naturally as matter collapses into filaments. Viewed in 3 dimensions, these voids resemble irregular polyhedra, with curved walls defined by the surrounding clusters. Their interiors are gently sloping, not uniform, with densities that rise gradually toward the edges. If you could slice through such a model, you'd see density contours that look like topographic lines on a map, the cosmic equivalent of hills and valleys, except that the height here represents matter density, and the valleys are regions of emptiness. In these simulations, the largest voids can reach diameters of hundreds of millions of light-years, sometimes approaching 1 billion. They're not static cavities, but dynamic zones of expansion. As the universe grows, matter continues to flow outward from the centres of voids toward the surrounding filaments. This motion, known as void expansion, is driven by the fact that regions of lower density experience less gravitational deceleration. In other words, space inside a void stretches faster than space in denser regions. Over cosmic time, this process causes the void to become even emptier and its boundaries to move outward, merging with neighbouring voids and reshaping the web around them. The KBC Void fits within this framework. Based on the measurements of galaxy density and motion in our local universe, it seems to be roughly 1 billion light-years in diameter and about 20 to 30% less dense than the cosmic average. Its boundaries appear to coincide with several major structures: the Perseus-Pisces supercluster, the Coma Wall, and parts of the Hercules-Corona Borealis region. These clusters form the edges of the void, marking where the underdensity gives way to the thicker filaments of the cosmic web. The centre of the void, where our galaxy likely resides, is relatively smooth and uniform, a calm patch in an otherwise turbulent landscape. One way astronomers test this picture is by examining the flow of galaxies around us. Inside a void, galaxies tend to move outward, away from the low-density centre and toward the denser walls. This pattern of motion is like the slow outward drift of air from a low-pressure zone in Earth's atmosphere. By measuring these flows, scientists can infer the shape of the void's boundaries. For the KBC Void, the flow pattern suggests a roughly spherical but slightly elongated structure, with one axis stretching toward the direction of the Virgo supercluster and another extending toward Perseus Pisces. The elongation reflects the uneven distribution of matter around our region. Gravity doesn't pull equally in all directions, so the void expands more easily along some axes than others. What's especially interesting about the KBC Void shape is that it may help explain subtle asymmetries in the cosmic expansion we observe. Because light from distant galaxies passes through regions of varying density on its way to us, the apparent brightness and redshift of those galaxies can change slightly depending on direction. If we live near the centre of an elongated void, light travelling through the thinner parts of the void would experience less gravitational delay, making galaxies in that direction appear slightly farther away or moving slightly faster. Conversely, light passing through denser boundaries would be more strongly affected by gravity, producing the opposite effect. These directional differences, though tiny, can influence precise measurements of cosmic parameters. It's worth noting that the concept of a centre within a void is somewhat abstract. Because the density changes gradually, there's no single point that marks the middle. Instead, astronomers define the centre statistically as the location where the density reaches its minimum value. In the case of the KBC Void, that point seems to be close to our position in the Milky Way, though not exactly aligned. The void may be offset slightly, meaning we sit not at the precise centre, but somewhere near it, within the inner third of the underdense region. This is enough to influence our local measurements, but not so extreme that it makes our vantage point unique or privileged. Dark matter plays a central role in defining the void shape. Though invisible, it provides most of the gravitational framework of the universe. In regions like the KBC Void, the density of dark matter is lower, which allows space to expand more freely. The distribution of dark matter can be mapped indirectly through gravitational lensing, the bending of light by mass. Observations of lensing across wide regions of the sky show patterns consistent with a large, smooth underdensity in our vicinity. These patterns don't draw sharp boundaries, but they reinforce the idea of a gently curved basin of low density surrounded by denser ridges. The presence of gas within the void adds another layer of complexity. Even in the emptiest regions, intergalactic gas remains, mostly hydrogen and helium left over from the early universe. In voids, this gas is thinner and cooler than in clusters, but it still emits faint radiation that can be detected at radio wavelengths. By measuring this background, astronomers can estimate how much normal matter exists within the void. The results suggest that, while the KBC Void is underdense, it's not devoid of matter altogether. It contains the faint glow of gas, the scattered light of distant galaxies, and the ever-present hum of the cosmic microwave background. When all these observations are combined, galaxy counts, gravitational lensing, peculiar velocities, gas measurements, the resulting picture of the KBC Void is one of gentle gradients rather than stark contrasts. The transition from void to filament happens gradually, over hundreds of millions of light years. The shape is not a clean bubble, but a soft, uneven depression surrounded by walls that ripple and bend with the weight of clustered galaxies. If you could trace it in 3 dimensions, it would look less like a sphere and more like an irregular ellipsoid, its contours moulded by the gravitational push and pull of nearby structures. Understanding this shape isn't just an exercise in cosmic cartography. It's essential for interpreting the data that define our view of the universe. The apparent acceleration of cosmic expansion, the precise value of the Hubble constant, even the observed distribution of supernovae, all depend on how light moves through space. If the space around us is slightly less dense, light travels through it differently, subtly altering the apparent scale of distant objects. Correcting for that effect requires an accurate model of the void's geometry. Without it, we risk misinterpreting what we see. Yet beyond the practical importance, there's something deeply compelling about the image of our galaxy floating near the centre of a vast asymmetric hollow. It evokes a sense of balance, a reminder that the universe's structure depends as much on emptiness as on matter. The shape of the KBC void is not a void in the everyday sense of the word. It's a form sculpted by the interplay of gravity and expansion, filled with the faintest traces of substance, alive with motion. Even the emptiest parts of the cosmos are in flux, their boundaries breathing slowly as the universe continues to evolve. The ongoing challenge for astronomers is to refine this picture with ever greater accuracy. Future surveys, like those from the Vera Rubin Observatory and the Euclid mission, will map the distribution of galaxies and dark matter across the sky in unprecedented detail. These observations will help define the true contours of the KBC void, its elongation, its depth, its relationship to surrounding structures. As the data improve, the lines on the cosmic map will sharpen, revealing not a perfect sphere but a complex landscape of density and flow. The shape of the hole that we inhabit, then, is both a literal and metaphorical reflection of the universe's character. It isn't static, it isn't absolute. It's a manifestation of motion, a region defined by how space itself stretches and bends. To grasp its shape is to recognize that even in what appears to be nothing, there is form, a geometry of absence that mirrors the structure of everything else. Gravity is usually thought of as a force of attraction, the invisible thread that binds matter together, shaping everything from falling apples to orbiting planets to the motions of galaxies. But in the vast, silent hollows of the universe, in the places where matter thins to a whisper, gravity takes on a different kind of role. It doesn't vanish, it simply changes character. In a void, gravity doesn't pull objects inward towards some central mass. It tugs outward, subtly, as though space itself were exhaling. This inversion, where emptiness seems to push rather than pull, is one of the most delicate and fascinating aspects of cosmic structure. Understanding how this happens requires thinking about gravity not as a force between objects, but as the shape of space itself, and how that shape changes when there's less matter around to curve it. Imagine, for a moment, a landscape made of flexible fabric, like a sheet stretched tight. Drop a heavy ball in one spot and the fabric dips downward, creating a well. That's how we often picture gravity. A mass bending space-time and pulling things toward it. Now, imagine lifting the ball out, leaving behind a slightly raised region where the fabric springs upward. That raised area isn't a hill in the usual sense, but a region where the curvature of space bends the opposite way. In the cosmic web, the dense clusters and filaments are like the wells, while the voids are like the lifted sections, regions where there's less curvature, less gravitational deceleration, and slightly faster expansion. This doesn't mean the void is actively repelling matter. It means that the surrounding regions of higher density pull harder, causing the space inside the void to expand more freely. In the case of the KBC void, the effect is vast but gentle. The difference in density between the inside and outside of the void is only a few tens of percent, yet stretched across 1 billion light years, that small imbalance becomes significant. The galaxies inside the void, including our own, feel slightly less gravitational pull from their surroundings than they would in an average region. As a result, they drift outward relative to the void's centre, sliding slowly toward the denser walls beyond. This outward flow is one of the defining signatures of void dynamics. It's not a violent motion. The speeds involved are on the order of a few hundred kilometers per second, minuscule compared to the speed of light, but over hundreds of millions of years, those small velocities add up, reshaping the distribution of galaxies and subtly influencing how we perceive cosmic expansion. This motion can be thought of as gravity's whisper, the quiet signal that even emptiness participates in the universe's dance. When scientists study these flows, they're listening for that whisper. They look for the tiny deviations in galaxy velocities that reveal how matter moves through space. In a dense region, galaxies tend to fall inward, their paths curving toward clusters. In a void, they do the opposite. accelerating outward along the gentle slope of the gravitational potential. The border between these regions acts like a watershed, separating the directions of flow. By mapping this pattern of motion, astronomers can infer the size, shape, and depth of the void itself. The physics behind this effect ties directly to Einstein's theory of general relativity. In that framework, gravity isn't a force acting across space, but the result of space-time curvature created by energy and mass. Where there's more mass, space-time curves inward. Where there's less, it curves outward. A void, then, is a region of relatively positive curvature, a place where space expands slightly faster because there's less mass to slow it down. Over cosmic timescales, this difference in curvature translates into real motion. Matter streams away from the void centre, and the void itself grows, merging with others to form larger underdense regions. The process is self-reinforcing. The emptier a region becomes, the faster it expands, and the faster it expands, the emptier it gets. This interplay between gravity and expansion is subtle, but essential for understanding the universe's evolution. In the early cosmos, matter was distributed nearly evenly, with only tiny fluctuations in density. Over time, gravity amplified those fluctuations, drawing material into dense regions and leaving emptiness in between. As the dense regions collapsed, their gravitational pull became stronger, accelerating the evacuation of matter from the surrounding voids. The result is the cosmic web we see today, a network of filaments and clusters surrounded by ever-growing hollows. Gravity in this context is not only the architect of structure, but also the sculptor of emptiness. It might seem paradoxical that less gravity in a region can cause matter to move outward, but that's because we usually think of motion relative to something fixed. In the expanding universe, there's no fixed backdrop. Space itself stretches, carrying galaxies with it. The rate of that stretching, the Hubble expansion, depends on the average density of matter and energy. In a void, where the density is lower, the local expansion rate is higher. The galaxies there aren't being pushed by some mysterious repulsive force. They're simply riding along with space that's stretching more quickly. From our perspective inside the KBC Void, that faster local expansion means that nearby galaxies appear to recede a bit more rapidly than the global average. This is one way the void's existence could contribute to the apparent discrepancy in the measured value of the Hubble constant. To visualize this, imagine dots drawn on a balloon. As the balloon inflates, the dots move apart. If one section of the balloon is thinner, it stretches faster than the rest, and the dots there separate more quickly. That's the relationship between voids and expansion. The void doesn't push the galaxies apart. It's simply an area where space stretches more rapidly because there's less mass to resist it. The boundaries of the void, where denser regions reside, stretch more slowly. Over billions of years, this differential expansion exaggerates the contrast, deepening the void and sharpening the surrounding walls. Astronomers measure this effect through careful analysis of galaxy redshifts and peculiar velocities. Redshift tells how fast a galaxy is moving away due to cosmic expansion. Peculiar velocity measures any deviation from that average expansion, caused by local gravitational influences. By comparing the two, scientists can identify patterns consistent with void dynamics. In the case of the KBC Void, galaxies at the edge of the region exhibit peculiar velocities that indicate outward motion relative to our position, as if space itself were flowing from a slightly overinflated bubble. The amplitude of this flow provides a measure of the void's gravitational profile, the degree to which it differs from the cosmic mean. What's remarkable is how consistent these observations are with theoretical predictions. Models of large-scale structure show that voids should expand faster than their surroundings, generating outward flows on the order of a few hundred kilometers per second. These flows have been detected not only in the KBC region, but also in other large voids across the universe, confirming that this behavior is a fundamental feature of cosmic evolution. The universe is not static even in its emptiest parts. the absence of matter does not mean the absence of motion. Dark energy complicates the picture further. This mysterious form of energy, which makes up roughly 70% of the universe, drives the acceleration of cosmic expansion. Its influence is uniform, but its effects become more pronounced in low-density regions. In clusters and filaments, gravity partially counteracts dark energy, slowing the local expansion. In voids, where gravity's grip is weaker, dark energy dominates, enhancing the stretching of space. This feedback loop means that voids are the places where the universe's accelerated expansion is most visible. They act as amplifiers of dark energy's effects, quiet test sites for the physics that governs the cosmos on its larger scales. Even light feels the whisper of gravity inside a void. As photons cross regions of varying density, their energy changes slightly due to the gravitational potential they encounter. Entering a void, light gains a tiny bit of energy, climbing down the slope of the potential. Exiting, it loses that energy again, but not perfectly symmetrically, because the void itself expands during the journey. The result is a minute net shift in the light's frequency, a phenomenon known as the integrated Sachs-Wolf effect. By studying these shifts in the cosmic microwave background, astronomers can detect the subtle imprint of voids across the sky. The KBC Void, being so large, could in principle leave a faint signature in that ancient light, though detecting it remains a technical challenge. The whisper of gravity inside a void is not only about motion and light, it's about perspective. Living inside an underdense region means that our reference frame, our sense of what's normal, is slightly biased. The galaxies around us may seem to follow the universal expansion, but the underlying curvature of space here is different from the average. This difference affects how we interpret distances, brightness, and time. Correcting for it requires precise cosmological modelling, an acknowledgement that even emptiness has measurable properties. There's a quiet irony in this. We tend to think of voids as the least active parts of the universe, but in some ways they're the most dynamic. Their boundaries shift, their interiors expand, and their influence extends far beyond their sparse contents. They are regions where the fabric of space reveals its flexibility, where the competing forces of gravity and dark energy find a delicate balance. Every void, including the one we may inhabit, is a kind of cosmic lung, exhaling slowly as the universe breathes. The study of void dynamics has grown into a major branch of cosmology precisely because it turns emptiness into a tool. By measuring the outward flow of galaxies and the distortions of light passing through these regions, scientists can test theories of gravity and dark energy that would otherwise remain abstract. Voids offer a clean environment, free from the complexities of dense clusters, where the fundamental physics of space-time can be observed with fewer distractions. They remind us that understanding the universe isn't just about counting stars. It's about listening to the silence between them. In the end, the pull of emptiness is less a force than a rhythm. It's the slow outward drift that balances the inward fall of matter elsewhere. Without that rhythm, the cosmic web would lose its coherence. The filaments would have no space to form, and the expansion of the universe would proceed differently. Emptiness, paradoxically, gives structure its shape. Gravity's whisper inside the KBC Void is the sound of that balance in motion, the quiet signal that even the absence of matter is part of the universe's ongoing conversation between fullness and nothingness. As we follow that whisper outward, the next question becomes how this gentle imbalance influences the larger behaviour of the cosmos. The tension between what we observe locally and what we infer globally, the puzzle of the differing expansion rates, lies at the heart of modern cosmology. The expansion of the universe is one of the most well-established facts in all of cosmology. We can see it written into the light of distant galaxies, each spectrum stretched toward the red as those galaxies recede from us, carried outward by the steady stretching of space itself. For almost a century, astronomers have measured that expansion, refining their techniques, building ever more precise instruments, and agreeing on nearly every detail except one: how fast it's actually happening. That seemingly simple question has become one of the most persistent puzzles in modern science, known as the Hubble tension. It's a disagreement between two methods of measuring the same thing, and it may hold clues not only to the structure of the universe, but also to the nature of time, space, and our place within them. The Hubble constant, named after Edwin Hubble, represents the rate of cosmic expansion, how much faster a galaxy moves away for every megaparsec of distance, where 1 megaparsec equals about 3.26 million light-years. When Hubble first calculated this number in the 1920s, his instruments were crude by modern standards, and his value was off by nearly an order of magnitude. Over the decades, improved observations refined the estimate, bringing it down to a range between 60 and 75 kilometers per second per megaparsec. For most of the 20th century, that was considered close enough. The uncertainty was large and the data were limited, but as technology advanced, the uncertainty shrank. By the early 2000s, astronomers expected to settle on a definitive number. Instead, the opposite happened. Today, there are two primary ways to measure the Hubble constant, and they don't agree. One method looks deep into the past at the early universe, using the cosmic microwave background, the faint afterglow of the Big Bang still detectable in every direction. Satellites like the Planck Observatory have mapped this background with exquisite precision, allowing cosmologists to infer the Hubble constant indirectly from the size and spacing of the temperature fluctuations imprinted on that ancient light. This early universe method yields a value of about 67.4 kilometers per second per megaparsec. The other method looks to the present, measuring the distances and velocities of relatively nearby galaxies using what are called standard candles, objects whose intrinsic brightness is well known, such as Cepheid variable stars and Type Ei are supernovae. By comparing their true brightness to their observed brightness, astronomers can calculate their distances, then compare those distances to their redshifts to determine the local expansion rate. This late universe method consistently gives a higher value, around 73. The difference of roughly 6 kilometers per second per megaparsec might not sound like much, but the error bars on both methods are now small enough that the two values don't overlap. Statistically, the disagreement is significant, beyond what could be explained by measurement error alone. This discrepancy is the Hubble tension, and resolving it has become one of cosmology's defining challenges. The question is whether the tension arises from new physics, something fundamentally missing in our understanding of the universe, or from subtler, local effects that distort our perspective. The KBC Void enters the discussion as one of those potential local effects. If we live in a region that's less dense than the cosmic average, then the expansion rate measured from within that region could naturally appear higher than the global value. The emptier space expands slightly faster, and the light from nearby galaxies reflects that faster local stretch. To see how this might work, imagine a rubber sheet marked with a grid. If you pull evenly on all sides, the grid expands uniformly, but if one patch of the sheet is thinner or under less tension, it will stretch more quickly than the rest. Observers living inside that thinner patch would see the grid lines moving apart faster than the average, even though the overall pulling force is the same. In cosmic terms, the thinner patch represents a void. The global expansion rate might be 67 kilometers per second per megaparsec, but inside the void, it could measure closer to 73, exactly the kind of discrepancy that defines the Hubble tension. Keenan, Barger and Cowie, when they first described the local underdensity that came to bear their initials, noted this possibility explicitly. Their calculations suggested that if our region of the universe were about 20% less dense than average, the local Hubble constant could be a few percent higher. Later studies refined the numbers but preserved the essence of the idea. A sufficiently large and deep void could account for part of the tension. The catch is that the required void would have to be enormous, on the order of 1 billion light-years across, and relatively symmetric around our position. The KBC Void fits those criteria loosely, though not perfectly. Some simulations show that its influence could raise the local expansion rate by 2 or 3%, reducing but not eliminating the discrepancy. That partial resolution is telling. It suggests that the Hubble tension may not come from a single cause but from several overlapping effects. The KBC Void could be one piece of the puzzle, a local bias layered atop broader physical processes. For example, if the early universe contained forms of energy or particles not accounted for in standard cosmology, those could also shift the inferred value of the Hubble constant. But even if new physics is ultimately needed to explain the full difference, understanding the local environment remains crucial. We can't measure the universe as though we're floating outside it. We measure from within, inside a gravitational landscape that shapes what we see. The mathematics behind these corrections is intricate, but the concept is simple. Light from a distant galaxy travels through billions of light-years of varying density before reaching our telescopes. Each region it passes through affects its journey, stretching it, bending it, altering its timing ever so slightly. If our local region is underdense, the light spends more of its journey in low-gravity space, meaning less time is lost to gravitational redshift. That small difference accumulates, making the galaxy appear slightly closer, or moving slightly faster than it would in a denser environment. When averaged across many galaxies, this bias raises the apparent expansion rate. The correction might seem negligible, but when your goal is to measure the universe's behaviour to within a few percent, every subtlety matters. What makes the Hubble tension more than just a technical argument is what it implies about our understanding of time and space. The Hubble constant isn't just a number, it's a measure of how quickly the universe grows, which means it's a measure of how time unfolds on cosmic scales. A higher Hubble constant implies a younger universe, around 12.8 billion years old, while a lower one suggests an older universe closer to 13.8 billion. A difference of 1 billion years may not seem enormous given the scale of cosmic history, but it fundamentally changes how we interpret everything from galaxy formation to the evolution of dark energy. In that sense, the Hubble tension is also a tension between two timelines, two versions of cosmic history that can't both be true in their current form. If the KBC Void is real, and its influence significant, it would mean that our local measurements are slightly accelerated versions of reality, a perspective skewed by the thinness of our surroundings. The universe itself wouldn't be expanding faster, it would just look that way from here. This wouldn't solve the entire discrepancy, but it would align the scales a little more closely, reducing the need for exotic explanations. It would also mean that our understanding of cosmic expansion depends intimately on where we are in the universe, a humbling reminder that observation and position are inseparable. However, not all cosmologists agree that the void hypothesis can explain enough of the tension. Some argue that even the largest plausible underdensity can only account for a fraction of the difference. The rest, they suggest, must come from new physics, perhaps an evolving form of dark energy, or an unknown type of particle influencing the early universe. Others maintain that the problem might lie in calibration, in how we measure distances to nearby galaxies or interpret the behaviour of standard candles. Each of these possibilities has passionate advocates and equally strong critics. The debate continues, precise and polite, a conversation carried out in journal papers and conference halls rather than confrontations. What makes the discussion especially intriguing is how it blurs the boundary between local and global perspectives. The Hubble constant is supposed to describe a universal property, the same everywhere, but the more precisely we measure it, the more variation we find. It's as if the universe resists being pinned down to a single rate of expansion, revealing instead a subtle patchwork, slightly faster here, slightly slower there. Voids, clusters and filaments all contribute to this texture, making the cosmos less like a uniformly inflating balloon and more like a fabric stretching unevenly under shifting tensions. The Hubble tension, then, is not merely a question of numbers, It's a window into the complexity of the universe's behaviour. It challenges the assumption that large-scale averages can fully describe reality. It suggests that local conditions, the density of our surroundings, the curvature of our space-time, the pathways light takes, matter in ways we're still learning to appreciate. If the KBC Void indeed exists and contributes even modestly to the discrepancy, it underscores how deeply embedded we are in the structures we study. We are not neutral observers looking out from a privileged vantage point. We are participants inside the experiment, shaped by the very phenomena we measure. To see the Hubble tension as a problem is to miss part of its significance. It's also an opportunity. Every major advance in cosmology has come from confronting contradictions, the mismatches between expectation and observation that force theories to evolve. The disagreement between early and late universe measurements might be pointing toward a deeper layer of truth, something that connects the geometry of space to the flow of time more intricately than current models allow. The KBC Void offers one possible bridge between those scales, a reminder that even something as subtle as a regional underdensity can ripple outward through our entire interpretation of the cosmos. Whether it accounts for a few percent or something more, its existence tells us that emptiness itself participates in the story of cosmic time. The tension between 67 and 73 is not just about numbers on a chart, it's about the relationship between where we are, what we see, and how we define the passage of cosmic history. And so, the whisper of gravity that began in emptiness leads directly to this paradox. A universe whose expansion seems to depend on who's measuring it, and from where. The search for resolution continues, but along the way it opens new questions about the nature of distance, motion, and observation. As astronomers refine their maps and models, they're not just trying to close a numerical gap, they're probing the fabric of reality itself. In the study of the cosmos, there are questions that can't be answered by direct observation alone. The scale is too vast, the timescale is too long, the distance is too extreme for light itself to show us the full picture. To understand the structure of the universe, how voids like the KBC form, evolve, and shape everything around them, scientists have turned to something that mirrors observation, but lives entirely in the realm of mathematics and computation, simulations. These are digital universes, immense in scope and intricate in detail, where every particle, every filament, every patch of emptiness evolves according to the same physical laws that govern reality. In these constructed worlds, silence can be studied, emptiness can be measured, and for the first time the invisible architecture of space becomes visible. Simulations of the universe begin with the same starting point that nature did, the early conditions after the Big Bang. Cosmologists take the observed properties of the cosmic microwave background, the faint glow left from the first 380,000 years of cosmic history, and use them as an initial map of density fluctuations. These fluctuations were tiny, 1 part in 100,000, mere ripples in a sea of near-uniform matter and radiation. But those ripples contained everything. They were the seeds of galaxies, clusters, filaments, and voids. A cosmological simulation takes those seeds and lets them grow, governed by gravity, expansion, and the known contents of the universe: ordinary matter, and dark energy. The first generation of simulations in the 1970s and 1980s were modest by today's standards, a few thousand particles evolving in a cube of space. They revealed hints of structure, faint webs beginning to form, but as computational power increased, so did ambition. By the early 2000s, projects like the Millennium Simulation could model more than 10 billion particles across a region of space, 2 billion light-years wide. The results were transformative. When the data were visualized, they showed a universe that looked strikingly familiar. Long filaments of matter weaving together like strands of fabric, clusters at their intersections, and immense voids filling the spaces between. the simulations confirmed what observations had begun to suggest, that the large-scale structure of the cosmos resembles a network, a cosmic web sculpted by gravity's long reach. For the first time, scientists could watch the process of cosmic evolution unfold in virtual time. They could see how small density fluctuations gradually amplified, how matter streamed along invisible threads into dense nodes, and how voids expanded as material drained from their centres. In these digital universes, voids were not static hollows but living structures. Their boundaries shifted, merged and reformed, driven by the slow flow of matter outward. This insight changed the way astronomers thought about emptiness. It wasn't a passive background, it was an active participant, constantly reshaping itself as the universe expanded. Modern simulations push this idea even further. They don't just model dark matter, which dominates the universe's mass, but also include baryonic matter, the gas, dust and stars that make galaxies shine. They incorporate feedback from supernovae and black holes, the turbulent processes that redistribute energy and matter on cosmic scales. This complexity makes the virtual cosmos more realistic, allowing researchers to compare simulated galaxies directly with real ones. When they do, the resemblance is uncanny. Spiral arms, galaxy clusters, cosmic voids, all emerge naturally from the same underlying physics. Within these simulations, voids like the KBC can be identified, measured and studied in ways that observation alone could never allow. Researchers can trace their histories, watching how they form from slightly underdense patches in the early universe, and how they evolve over billions of years. The process is gradual. As matter flows out, the void becomes emptier, and its walls grow sharper. Neighbouring voids merge, creating vast underdense regions that span hundreds of millions of light years. By the present epoch, most of the universe's volume is taken up by these expanded voids, connected by thin filaments of matter that contain nearly all the visible galaxies. The simulations reveal patterns that match what we observe around us. The size distribution of voids follows a predictable trend. Small voids are common, large ones rare. The largest tend to form in regions where the initial density fluctuations were weakest, giving rise to enormous shallow basins in the cosmic web. The KBC Void fits naturally into this hierarchy. It's not an anomaly, but a typical feature of cosmic evolution, magnified by scale and perspective. If we truly live near its centre, that's not a special circumstance. It's a reflection of how structure forms across the universe. Every large-scale map, real or simulated, shows similar hollows scattered across the cosmic foam. One of the most powerful aspects of simulations is their ability to test hypotheses about unseen physics. By adjusting the parameters, the strength of dark energy, the behaviour of dark matter, the initial spectrum of fluctuations, scientists can see how the virtual universe changes. If a simulation reproduces the observed large-scale structure, including voids and filaments, it suggests that the underlying physics is correct. If it doesn't, the model must be revised. In this way, simulations serve as both laboratory and mirror, showing us how small changes in the laws of nature might ripple outward, across billions of years and billions of light years. For example, one of the ways researchers test the void hypothesis related to the Hubble tension is by inserting a local underdensity into their simulated universes. They create a region about 1 billion light-years wide, reduce its matter density by 20 or 30%, and place a virtual observer within it. Then they measure the expansion rate from that observer's perspective. The result is consistently the same. The local expansion appears faster than the global average. The amount of acceleration depends on the depth of the void, but the trend is clear. Living inside an underdense region naturally raises the measured Hubble constant. These virtual experiments lend credence to the idea that the KBC Void could contribute to the observed discrepancy, even if it can't explain it entirely. Beyond testing specific theories, simulations also offer something more profound, a way to visualize the invisible. In the raw data, a void is just a pattern of numbers, a series of density values spread across 3 dimensions. But when rendered into images or animations, those numbers become landscapes. You can see the delicate filaments connecting clusters, the vast cavities of emptiness between them, the slow motion of expansion. Some simulations even color code matter density, turning the universe into a glowing map of light and shadow. Blue for emptiness, gold for density, red for the fiery centers of clusters. Watching one evolve is like watching a living organism breathe. In these digital reconstructions, silence becomes visible. The emptiest regions, which seem like nothing at all, take on form and motion. Their boundaries pulse as matter flows, their centers drift as expansion continues. When viewed over billions of simulated years, voids appear to grow, like bubbles rising through a cosmic fluid, merging and blending until the web of the universe looks more like a network of expanding hollows than of clustered matter. The galaxies, though luminous, occupy only the thin surfaces between voids, a fragile scaffolding stretched across a sea of emptiness. What makes this visualization so striking is that it mirrors the mathematics of reality. The equations that describe the growth of structure, the Poisson equation for gravity, the Friedmann equations for expansion, the continuity equations for matter flow, are all encoded in these models. Every movement of a simulated galaxy, every widening of a void, is a direct consequence of those laws. When you watch a void expand in a simulation, you're seeing the mathematics of the universe turned into motion, the invisible logic of gravity rendered as a visual rhythm. These virtual explorations also reveal the subtle diversity of void shapes. Some are nearly spherical, others elongated or flattened by the gravitational influence of nearby filaments. Many overlap, forming chains and networks of emptiness that extend far beyond what any single observation can capture. The KBC Void, as represented in simulations, appears as one of these linked hollows, not an isolated bubble, but part of a continuum of underdensity stretching through our local cosmic environment. Its boundaries merge seamlessly with neighbouring voids, reinforcing the idea that cosmic emptiness is not compartmentalized but continuous. Simulations also allow scientists to experiment with perspective. By placing virtual observers in different parts of the simulated universe, researchers can see how local conditions affect measurements of cosmic parameters. Observers inside dense clusters perceive a slightly slower expansion, while those in voids measure a faster one. This variation underscores a key point. The universe is not uniform from every vantage point, even if it appears statistically uniform on the larger scales. The KBC Void, as seen from our position, is a reminder of that local bias, a difference that simulations make clear in a way no static map could. The evolution of these digital universes continues to advance alongside computing technology. Modern projects like illustrious TNG, Eagle, and Millennium XXL use supercomputers with thousands of processors, running for weeks or months to compute the gravitational interactions of billions of particles. Each simulation produces terabytes of data, a virtual cosmos so detailed that it can take years to analyze fully. In these digital archives, scientists explore the growth of galaxies, the expansion of voids, and the flow of dark matter with the same rigor that experimental physicists study particles in a laboratory. The difference is scale. Their laboratory is the universe itself recreated in code. What's most surprising, though, is how familiar these simulated universes feel. The patterns they produce, clusters of light surrounded by expanding darkness, are the same patterns that fill the night sky. The silence of a void, when visualized, isn't truly silent. It's filled with the motion of space itself, the faint echo of gravitational fields shifting as matter flows. The term simulation of silence becomes something of a paradox. The emptiness isn't absence, it's activity without noise, motion without collision. It's the stillness of a system that never stops evolving. For cosmologists, these simulations are more than just tools. They're windows into the unseen. They allow theories to be tested, intuition to be refined, and questions to be asked that observation alone could never pose. They show that the universe, even at its quietest, is dynamic, a structure in constant motion, sculpted by gravity and expansion. The KBC Void, when viewed through this lens, isn't a strange anomaly, but part of that grand evolution, a single hollow in the cosmic symphony of structure and silence. From these virtual perspectives, the path forward becomes clearer. If simulations can reproduce the shapes, flows, and effects of voids like ours, they can also predict what we should observe next, where light should bend, how galaxies should move, what signatures the void should leave on the cosmic microwave background. Step by step, observation and simulation converge, each refining the other. The silence of the void, once a mystery, becomes a measurable, modelable feature of the living universe. Once the silence of space can be seen, the question turns inward again, to what it means for us, living within such a hollow, to occupy this kind of space. Are we special for existing in a cosmic valley, or are voids like ours so common that they define the universe's balance? The simulations offer the data, but the meaning, as always, lies in the interpretation. In every era of science, there's a question that seems to return no matter how far we think we've come. Are we special? It began when humans first looked up and believed the stars revolved around Earth. It resurfaced when telescopes revealed the Earth revolved around the Sun, and again when galaxies were discovered to exist beyond the Milky Way. Each time the answer grew a little more humbling. We were not at the centre, not unique, not privileged. Yet even as that lesson became part of our understanding, we've never quite stopped asking. Every new discovery about the universe carries within it a quiet echo of that old question. And the idea that we might live inside a cosmic void brings it back once more, though now the question feels subtler. Is our place in the KBC Void a coincidence? Or does it tell us something deeper about the universe's design? The Copernican principle, named for the astronomer who dethroned Earth from the centre of the cosmos, has guided cosmology for centuries. It states that we do not occupy a special position in space. The universe, on its largest scales, should look roughly the same no matter where you stand or in which direction you look. This principle has proven incredibly powerful, allowing scientists to model the universe as homogeneous and isotropic, smooth when viewed from afar, even if clumpy up close. That assumption underlies the entire framework of modern cosmology, but it also comes with a catch. If you find evidence that your surroundings differ significantly from the cosmic average, you have to ask whether the principle still holds, or whether your view has been quietly biased by your environment. The KBC Void sits precisely at that crossroads. If we truly live in a region that's less dense than average by 20 or 30%, extending across 1 billion light years, does that make us special? Not in the sentimental sense, but in the scientific one. Does it mean our measurements of the universe are skewed in ways that others wouldn't experience? And if so, does that uniqueness violate the spirit of the Copernican principle, or simply illustrate that even principles have to be applied with care? The first thing to understand is that voids are not rare. They make up most of the universe's volume. For every bright filament or dense cluster, there are vast expanses of near-nothingness. The cosmic web is mostly holes connected by threads of matter. Statistically, it's inevitable that some galaxies, and therefore some observers, will find themselves inside underdense regions. In fact, simulations suggest that roughly half of all galaxies exist in environments less dense than average. The KBC Void, while large, is not exceptional in kind, only in scale. 1 billion light-years is big, but it's not unprecedented. Other voids, like the Butter's Void and the Dipole Repeller, are comparable or even larger. From that perspective, living inside one is not a sign of cosmic privilege, but an ordinary outcome of how the universe structures itself. Still, the coincidence is striking. If the KBC Void's existence does influence our local measurements, subtly altering how we see expansion, how we interpret the brightness of supernovae, how we calculate distances, then we happen to occupy a position with measurable effects on our understanding of the cosmos. That might feel like a special vantage point, but it's not designed for us. It's simply where we happen to be. The universe is large enough to accommodate every possibility, and given enough volume, some observers were bound to find themselves near the centres of such voids. The odds are low, but in a universe of trillions of galaxies, low odds still guarantee outcomes somewhere. We're not special in the sense of being chosen. We're just one realization among countless others. Yet there's another way to look at it. The very fact that we can notice the void at all, that we have the tools to map galaxies across billions of light years, to measure redshifts, to simulate the structure of space, is remarkable. Not because it makes us central, but because it makes us conscious participants in the universe's unfolding. We've reached a point where the human mind, through mathematics and observation, can trace the outlines of the emptiness it inhabits. The coincidence that our galaxy sits inside a massive underdensity might not make us cosmically special, but it does make our perspective scientifically meaningful. The KBC Void becomes not a privilege, but a window, a natural experiment in how cosmic structure influences perception. Philosophically, there's something elegant about this position. The Copernican principle doesn't say we can't live in interesting places. It says we shouldn't assume those places were made for us. If voids are a normal part of the cosmic landscape, then someone has to live in them, and their experiences, their measurements, their interpretations of the universe will reflect their environment. In that sense, we're not breaking the Copernican rule. We're demonstrating it. The universe looks the same everywhere, not because every observer sees the same density, but because every observer's experience is shaped consistently by the local structure around them. The view from a cluster or a void may differ, but the laws governing those differences remain the same. Still, the human instinct to look for meaning in coincidence is hard to resist. It's natural to wonder whether our presence in this particular void carries some significance beyond statistics. After all, voids are quiet places. Galaxies inside them evolve more slowly, forming stars at a gentler pace, untroubled by the frequent collisions and interactions that shape galaxies in denser environments. The Milky Way is a stable spiral galaxy with a long, calm history. Perhaps its relatively peaceful surroundings helped make that possible. In a more crowded region, constant gravitational encounters might have disrupted its structure, or triggered intense bursts of star formation, altering the conditions that eventually allowed planets and life to emerge. This line of thinking enters the realm of what's known as the anthropic principle. The idea that our observations of the universe are conditioned by the fact that we exist within it. In other words, the universe must have properties compatible with our existence, because if it didn't, we wouldn't be here to observe it. The anthropic principle can sound circular, but it captures a simple truth. Life arises only in environments that permit it. If our galaxy's location inside a void contributed to its long-term stability, then our existence is not independent of that cosmic geography. It doesn't mean the void was made for us. It means we could only have emerged in a place where the conditions happened to be right. The notion that the KBC Void might have played a quiet role in the story of our existence is speculative but not unreasonable. The Milky Way's calm history of star formation, the relative isolation of the local group, the long periods of stability in our solar system's orbit around the galactic centre, all these features might in part reflect the tranquil gravitational environment of an underdense region. In a universe shaped by density and motion, even emptiness can influence the course of history. If our position has helped shield us from cosmic chaos, then the void has, in a sense, been a silent participant in the evolution of life. But that's not the same as being chosen or unique. It's simply an intersection of circumstance and possibility. Every galaxy, every star, every planet exists within a web of causes, stretching back to the universe's beginning. The patterns of density that form the KBC Void were set long before the Earth existed, long before life arose to question its significance. The fact that we now have the capacity to measure those patterns, to notice the void's influence, and to reflect on its meaning is part of the same story. The observer and the observed are not separate. They're connected by the physics that governs both. When cosmologists debate whether our position violates the Copernican principle, they often conclude that it doesn't. Statistical analyses show that living in an underdense region as large as the KBC Void is improbable, but not implausible. The probability might be 1 in a few hundred, perhaps 1 in 1,000. Unlikely, yes, but not impossible. In a universe with billions of galaxies and countless potential observers, even rare outcomes will occur somewhere. We just happen to be one of them. The same reasoning applies to many of the coincidences that define our world: the sun's distance from Earth, the chemistry of carbon, the timing of cosmic evolution. Each could seem extraordinary in isolation, but in the vastness of the cosmos, extraordinary becomes inevitable. There's a quiet comfort in that perspective. We don't need to be special to find meaning. The fact that we exist at all, in a universe capable of producing both life and the emptiness that surrounds it, is wonder enough. Living in a void doesn't make us central or chosen. It makes us part of a broader pattern, one that includes both the bright threads of galaxies and the dark spaces between them. If anything, our position emphasizes how thoroughly we belong to the universe's structure. We are products of its laws, its accidents, its balance between fullness and absence. Perhaps that's what makes the KBC Void such a powerful idea. It turns the notion of cosmic emptiness into a mirror, reflecting not isolation, but participation. We're inside a vast hollow, not because we were meant to be, but because the universe's natural process of expansion and clustering made such hollows inevitable. Our presence here is an outcome of physics, not destiny, and yet knowing that doesn't make it any less extraordinary. To be aware of the void is to be aware of context, to understand that our existence is embedded in the texture of the cosmos, shaped by forces we can barely imagine. Whether we call that luck or inevitability doesn't change the reality. We are here, on a small planet in a quiet galaxy, adrift in a billion light-year basin of thin space. The fact that we can ask whether that makes us special is answer enough. It makes us conscious, curious, and connected. When you hear the word void, it's easy to imagine distance, a gulf, an absence, a separation. The term itself invites the feeling of isolation, of being adrift in an unlit ocean, and yet the strange truth of living inside a cosmic void is that we're not alone, not even remotely. The KBC Void may stretch across 1 billion light-years, and the average distances between galaxies within it may be greater than in denser regions, but gravity, light, and time still weave everything together. The universe doesn't recognize isolation in the way we do. Its vast emptiness is threaded with connection, even where the density drops almost to nothing. The illusion of isolation comes not from the void itself, but from the limits of our perspective, from what we can see, and from how we interpret what that seeing means. When astronomers describe our cosmic environment as underdense, they're not saying there's nothing around us. On the contrary, the Milky Way alone contains hundreds of billions of stars, most with their own planetary systems, all orbiting together in an enormous disk over 100,000 light-years wide. Around it, the local group forms a miniature cosmos of its own, dozens of galaxies bound together by gravity, interacting, exchanging matter, and drifting as a single unit through space. Beyond that, the Virgo supercluster, Laniakea, and the great walls of the cosmic web surround us on all sides. Even in the depths of the KBC Void, galaxies shine, clusters gather, and filaments stretch faintly through the dark. There is no true isolation here. There is only spacing, a gentler distribution of presence. The human mind isn't naturally built to grasp scales like this. Our instincts are tuned to environments where distances can be crossed in moments or hours, not in millions or billions of years. When we read that the nearest large galaxy, Andromeda, is 2.5 million light-years away, the number feels like a wall, an unreachable gulf that separates us from everything else. But light itself crosses that gulf continuously. Photons leave Andromeda every moment, travel through the thin intergalactic medium, and arrive here as faint signals recorded by telescopes or by our own eyes under a dark sky. The fact that we can see Andromeda at all proves that the space between us is not empty in the way emptiness is imagined. It is transparent, transmissive, alive with motion. What makes the KBC Void seem so immense is not the physical distance but the contrast. In denser parts of the universe, galaxies are packed tightly together, separated by only a few million light-years. Here, the gaps are wider, the clusters smaller, the filaments more delicate. It's a slower, quieter neighbourhood, not an abandoned one. Even within voids, faint structures persist. Small groups of galaxies, wisps of gas, traces of dark matter. They form a kind of ghostly framework that maintains the continuity of the cosmic web. The illusion of emptiness arises because our senses and even our instruments can only detect the brightest parts of that web. The faintest threads are invisible to us, hidden beneath the sensitivity of our detectors. In reality, the void is less like a blank canvas and more like a watercolour, gradients of density blending seamlessly into one another. Astronomers have found that galaxies inside voids are often different from those in crowded regions. They tend to be smaller, bluer, and more actively forming stars. The reason is simple. Isolation in a cosmic sense gives them time. Without the frequent mergers and interactions that drive the evolution of cluster galaxies, void galaxies can evolve more peacefully. They slowly convert their gas into stars, maintaining their disks and spiral arms for longer. These galaxies, though fewer in number, create their own small communities. The gravitational bonds between them persist for billions of years, and their shared motion through space ties them together like members of a drifting archipelago. Even in the most underdense regions, matter finds ways to connect. The same is true on grander scales. The gravitational influence of the surrounding filaments and walls extends deep into the void. Space itself may expand more quickly here, but gravity's reach doesn't vanish. Every particle of matter in the KBC Void still feels the combined pull of everything beyond its boundaries. That pull shapes the trajectories of galaxies, directs the flow of gas, and determines how light bends as it passes through. The void's emptiness is therefore not an absence of influence, but an environment defined by gentler forces. If the dense regions of the universe are the crowded cities of the cosmic landscape, voids are the open plains, quieter perhaps, but still part of the same terrain. One of the most profound ways the illusion of isolation breaks down is through light itself. Light from distant galaxies doesn't stop at the edges of the void. It travels through it. The photons arriving at our telescopes tonight have crossed billions of light years, moving through countless regions of varying density, passing through the cosmic web's filaments and voids alike. Along the way, they record those encounters in subtle ways, shifts in energy, slight deflections, delays in arrival time. By studying those signals, astronomers can reconstruct the unseen structure between us and the source. Every beam of light that reaches us is, in a sense, a message from across the void, a connection that spans time as well as space. Even the cosmic microwave background, the oldest light in existence, carries the imprint of these connections. It fills every corner of the universe, passing through every void and cluster, bearing the faint scars of its journey. When we measure tiny fluctuations in that ancient radiation, we're not just looking at the early universe, we're seeing the accumulated effect of billions of years of interaction between light and structure. The void is part of that story, shaping the way this background light reaches us. It's another reminder that isolation in cosmological terms is never total. Every part of space communicates with every other through the propagation of light and the pull of gravity. This interconnectedness challenges our everyday intuitions about separation. On Earth, isolation feels absolute. A wall blocks sound. A distance ends a conversation. A room can hold silence. In space, none of that applies. Even silence is full of activity. Particles of light, cosmic rays, and waves of gravity move continuously through every cubic centimetre of space. The so-called vacuum is never truly empty. It seethes with quantum fluctuations, tiny bursts of energy appearing and vanishing in less than a trillionth of a second. The deeper we look into emptiness, the more structure we find. The illusion of isolation fades into a recognition that nothing in the universe ever stands apart. The KBC Void, for all its immensity, obeys this same principle. It may expand slightly faster than the surrounding regions, but it remains bound within the universal network of motion and energy. Its walls are connected to others. Its gravity interacts with the gravity of everything else. Light from the far side of the void passes through its interior, reaches our instruments and continues on. If you could trace the path of a single photon from a galaxy beyond the void to the lens of a telescope on Earth, you'd find that it never travelled through truly empty space. Along its route, it would have crossed clouds of hydrogen, faint intergalactic dust, and the curved geometries created by distant masses. Even the emptier stretches of the void are permeated by the residual fingerprints of creation. Our perception of cosmic isolation is further complicated by the fact that the light we see is old. When we observe a galaxy a billion light-years away, we're seeing it as it was a billion years ago. The emptiness between us isn't static, it's expanding, evolving, changing shape. The photons we detect left their sources long before the Earth had taken its current form, and the space they crossed has grown during their journey. What we see as isolation is really a layering of times, not distances, a sequence of moments frozen in light. The universe we observe is a record of interactions that have already happened, not a snapshot of stillness. The apparent separation between objects is partly an illusion created by the time it takes for their light to reach us. This perspective transforms how we think about the void. Instead of imagining ourselves as solitary beings floating in an empty bubble, we can see ourselves as part of a continuous process, connected across scales, times and spaces by the same fabric that binds the universe together. The void isn't a boundary, it's a medium. It's the quiet space through which the messages of the cosmos travel. The KBC Void might slow the formation of galaxies and thin the density of matter, but it cannot stop the flow of information, energy or influence. Every photon that crosses it carries a link between one corner of the universe and another. In that sense, the illusion of isolation is as much psychological as it is physical. From our small, fragile world surrounded by incomprehensible darkness, it's natural to feel alone. But the truth, borne out by every equation and every observation, is the opposite. We're connected to the entire universe through gravity, through light, through time itself. Even the emptiness between galaxies participates in that connection. The void is not a separation but a structure, a quieter, slower form of the same cosmic conversation that fills the crowded clusters. It's strange, almost poetic, that the region we call empty may be the one that best reveals how connected everything truly is. The KBC Void, vast and gentle, stretches across our cosmic neighbourhood like a slow breath, but within that breath are all the bonds that hold the universe together. What we perceive as solitude is simply a quieter kind of belonging. The universe has never stopped changing. From the moment it burst into being, it has been in motion, expanding, cooling, structuring itself, transforming from an almost perfectly smooth sea of energy into the intricate landscape of galaxies, clusters, and voids that we see today. That evolution didn't end billions of years ago. It continues even now. Every filament that stretches between clusters, every star that forms and dies, every empty basin of space that slowly expands, all a part of the same process. When we look at the KBC Void or any of the countless other hollows scattered through the cosmic web, what we're really seeing is an evolutionary snapshot, one stage in the life cycle of the universe's great voids. These vast spaces are not static gaps. They are living components of cosmic evolution, growing and changing with the rhythm of expansion itself. The early universe was astonishingly uniform. The cosmic microwave background, the relic radiation from when the universe was only a few 100,000 years old, shows that the density everywhere was nearly the same, differing by less than 1 part in 100,000. Those tiny fluctuations, minute variations in density seeded by quantum fluctuations during inflation, were the starting points for everything that followed. Regions just slightly denser than average began to collapse under their own gravity, gathering matter into knots that would one day become galaxies and clusters. Regions that were slightly less dense did the opposite. As the denser areas drew in more material, the underdense areas lost it, stretching and thinning as matter flowed outward. The voids were born at the same moment as the galaxies, their fates intertwined from the very beginning. As billions of years passed, gravity and expansion played out their slow tug-of-war. In the densest regions, gravity dominated, pulling gas, dark matter and radiation together to form stars and galaxies. In the emptiest regions, expansion won. Space itself stretched faster where there was less mass to hold it back, and the voids expanded. The process fed on itself. The emptier a region became, the faster it expanded, and the faster it expanded, the emptier it grew. This feedback loop led to the formation of immense cavities, the dark hollows between the bright filaments of the cosmic web. Computer simulations of the universe's evolution show this process with astonishing clarity. Starting from near-uniform conditions, the models evolve forward under the laws of gravity, hydrodynamics, and cosmic expansion. Within a few 100 million years, faint filaments begin to appear. By 1 billion years, those filaments have thickened into visible threads, while the regions between them start to widen. By 5 billion years, distinct voids fill most of the volume, pushing the matter into an intricate sponge-like pattern. The process doesn't stop there. Even now, 13 billion years later, the voids continue to grow. Matter still flows out of them, pulled toward the walls and clusters at their edges. The universe becomes ever more structured, yet also ever more empty, as the spaces between the threads widen. Voids grow not by expanding into nothingness, but by the redistribution of matter. The expansion of space affects all regions equally, but the local dynamics depend on density. In a dense cluster, gravity slows expansion. In a void, the lack of gravity allows expansion to proceed faster. Over time, this differential motion causes matter to drift from the interiors of voids toward their peripheries. The process resembles the way bubbles form and rise in a boiling liquid. Small voids appear first, then merge into larger ones separated by thin walls of remaining matter. Eventually, the largest voids dominate, swallowing the smaller ones in a process cosmologists call void hierarchy. The KBC Void, if confirmed in detail, would represent one of the upper tiers of this hierarchy, a mature void formed by the merging of many smaller underdense regions over billions of years. Dark energy adds another dimension to this story. About 5 billion years ago, the universe entered a new phase in which the expansion began to accelerate. This acceleration, driven by dark energy, changed the balance between matter and emptiness. Gravity still pulls matter into clusters, but dark energy pushes the universe apart on the larger scales. The effect is especially strong in voids, where gravity's influence is weakest. As a result, the voids expand faster than ever before. In simulations that include dark energy, the contrast between dense and empty regions increases sharply over time. the walls of the cosmic web become more pronounced, while the interiors of voids stretch and smooth out. It's a quiet amplification of difference, the universe emphasizing its own structure through acceleration. The rate at which voids grow offers cosmologists a way to measure the properties of dark energy. By comparing the observed distribution of void sizes and shapes at different epochs to predictions from simulations, scientists can test whether the acceleration matches the expectations of Einstein's cosmological constant or requires new physics. In this way, the hollows of the universe act as laboratories for its most mysterious component. The KBC Void, sitting in our cosmic backyard, provides a particularly interesting test case. Its depth and expansion rate could hold clues about how dark energy behaves on intermediate scales, neither purely local nor fully global. Despite their reputation as regions of nothing, voids are not devoid of evolution. Inside them, galaxies continue to form, albeit more slowly. These void galaxies often have unique characteristics. They tend to be rich in cold gas, lightly populated by stars, and largely undisturbed by mergers. In some cases, they exhibit extended disks or unusual morphologies, their shapes preserved by the absence of strong gravitational encounters. Over billions of years, these galaxies drift apart, following the general expansion of the void. Their light, stretched by the faster local expansion, carries the signature of that motion. When astronomers measure their redshifts, they're recording not only the global expansion of the universe, but also the local breathing of the void itself. The edges of voids evolve differently. There, gravity and expansion reach a kind of balance. The walls of the cosmic web, the filaments and sheets where matter collects, are where galaxies cluster and superclusters form. These boundaries thicken over time as matter continues to flow in. The process is self-organizing. Voids push matter outward, walls draw it in, and together they maintain the universe's large-scale pattern. It's a dynamic equilibrium that will continue for as long as expansion persists. Over immense timescales, the voids will grow so large that the filaments between them may stretch thin, but the structure itself will remain recognizable, a frozen echo of the web we see today. Looking into the future, cosmologists can use simulations to predict how this evolution will continue. If dark energy remains constant, the universe will keep accelerating indefinitely. The voids will expand faster and faster, and the filaments will recede from one another until even the nearest clusters drift beyond reach. Over tens of billions of years, the observable universe will shrink from our perspective, not because space stops expanding, but because light from distant galaxies will no longer be able to reach us. The universe will appear to empty out. Future observers, if any remain, might see only the galaxies bound within their own local group, unaware that beyond their horizon lies a vast web that once connected everything. In that distant future, the voids will dominate entirely. The large-scale structure we now see will persist only in the frozen memory of simulations and the fossilized patterns of the cosmic microwave background. But even that imagined loneliness is an illusion born of perspective. The expansion that isolates galaxies also preserves the information of their connection. The gravitational imprints left by the structure, the way voids shape the cosmic microwave background, the way they bend light through gravitational lensing, will remain detectable in principle. The universe will continue to carry the record of its own formation, even as its visible components drift apart. The story of cosmic evolution, then, is not a story of loss, but of transformation. The same processes that create emptiness also create structure. The holes that grow are not mistakes or absences. They're integral features of the universe's design. The KBC Void, viewed through this lens, becomes a chapter in a much larger narrative. Its existence, if confirmed, is a sign of the universe's natural tendency toward contrast, the coexistence of density and emptiness, attraction and expansion. The void's growth over billions of years mirrors the broader evolution of the cosmos, from a nearly uniform beginning to a rich, textured complexity. The universe doesn't simply expand, it differentiates, carving out structure through imbalance. Each void, including ours, is a product of that ongoing differentiation. Even now, the growth continues. Matter still flows outward, the filaments still stretch, and the boundaries of the KBC Void shift slowly over time. To us, these motions are imperceptible, but over cosmic timescales they are profound. The distances between galaxies increase, the density decreases, and the void's expansion subtly alters the background against which we measure all things. The universe we see today is a temporary configuration, one frame in an endless sequence of change. It's remarkable to think that this constant transformation arises from the simplest ingredients: gravity, energy, and time. The laws that govern the smallest particles also govern the largest structures, and from those laws emerges a self-organizing system of extraordinary beauty. The wholes that grow are not failures of creation, but its expression. They are the spaces that make structure possible, the dark balance that allows light to shine. Understanding this helps place our cosmic position in context. The KBC Void isn't a cosmic anomaly to be solved. It's a manifestation of the universe's natural rhythm. Its growth is part of the same process that formed the Milky Way, that built the galaxies, that stretches light itself. The cosmic web, with its vast balance of fullness and emptiness, is a single, evolving entity, and we are part of its unfolding. The story doesn't end with the present moment of growth. The universe will continue to evolve long after every star we know has faded. The voids will expand, the filaments will thin, and the patterns we map today will become the quiet memory of a time when everything was closer together. But even then, the principles that shape the KBC Void, gravity, motion, and the geometry of space, will still be at work. The cosmos will keep its balance, its silent conversation between matter and nothingness. When you think about emptiness, the first instinct is to equate it with absence. A lack of matter, a lack of light, a lack of life. But the more we learn about the universe, the more that idea begins to unravel. The great voids of the cosmos, like the one we live in, are not dead zones. They are dynamic, structured, and quietly essential. They give shape to everything that exists. Without emptiness, there would be no contrast, no direction for gravity to pull, no place for galaxies to form and evolve. In their silence, the voids reveal something profound about balance, motion, and the way complexity arises from simplicity. To study a void is to study the conditions that make structure possible, and by extension, the conditions that make understanding possible. When astronomers first began mapping the universe's large-scale structure, the discovery of voids was unsettling. The early models of cosmology imagined a smooth, even distribution of galaxies, like grains of sand spread uniformly across a beach. Instead, the observations revealed an intricate web, clusters and filaments separated by immense regions of near emptiness. At first, the voids were treated as gaps in the data, as if something were missing. But over time, the realization grew that these hollows were not accidents. They were a natural consequence of the same laws that shaped everything else. The universe organizes itself through contrast, regions of attraction surrounded by regions of release. The balance between fullness and emptiness is what gives the cosmos its coherence. That same principle applies far beyond astrophysics. Emptiness is not the opposite of existence. It's part of its structure. The spaces between things define their relationships. In art, silence gives shape to music. In writing, spaces between words allow meaning to emerge. In human life, pauses make experiences distinct. Without the intervals, everything would blur together. The voids of the universe operate in a similar way. They separate the clusters, giving them form and scale. They provide the quiet background against which the drama of galaxies unfolds. The more we look at them, the more we realize that they are not the absence of reality, but one of its expressions. Even on a physical level, emptiness is never truly empty. The vacuum of space is filled with fields and fluctuations. Quantum physics tells us that even the most perfect vacuum seethes with virtual particles, appearing and disappearing in fractions of a second. Space hums with the faint residue of energy, the zero-point field that underlies all things. When light travels through a void, it is influenced by this restless background. The photons shift and stretch, interacting subtly with the geometry of space itself. The void is not a blank canvas. It's an active medium, shaped by forces we are only beginning to understand. To live inside such a vast hollow, to realize that our entire galaxy is part of a structure defined by thinness, is to be confronted with the scale of contrast that sustains the universe. The Milky Way, brilliant and complex, drifts through an environment where the average density is lower than the cosmic mean. It's a reminder that even something as intricate as a galaxy arises from imbalance. The universe does not seek uniformity. It thrives on difference, on the dance between density and emptiness. The voids teach us that equilibrium is not stasis, but motion, a dynamic balance where both presence and absence have roles to play. This lesson resonates deeply when we consider how structure evolves. In the early universe, everything was almost uniform, and it was that near uniformity that made change possible. Slight deviations, the faintest ripples in density, were enough to set everything in motion. If the universe had been perfectly smooth, nothing would have formed. There would be no galaxies, no stars, no planets, no life. The voids, born from those small differences, are reminders that perfection is sterile. It's irregularity, imperfection, and unevenness that make creation possible. As the universe ages, those differences become more pronounced. The dense regions grow denser, and the empty regions grow emptier. On human timescales, the change is invisible, but over billions of years, the voids expand, the clusters contract, and the pattern of the cosmic web becomes sharper. The same physical processes that create galaxies also create silence. The two are inseparable, mirror images of the same laws expressed in opposite directions. Emptiness is not a void in the human sense. It's a state of minimal interference, where the forces that shape the universe reveal their underlying simplicity. There's something deeply grounding about recognizing that the universe's structure depends on what isn't there as much as on what is. In cosmology, the presence of a void changes how light travels, how matter moves, how time unfolds. In life, the presence of quiet changes how we think, how we perceive, how we feel. The emptiness of space and the quiet of thought are both conditions for clarity. The vast hollows between galaxies remind us that even the grandest systems are built on contrast, and that balance doesn't mean uniformity but harmony among opposites. If we translate this idea back into human experience, it becomes almost meditative. The universe, by its nature, teaches the value of stillness. The voids, immense and unhurried, expand in silence, shaping the motion of everything around them without needing to contain anything themselves. They show that influence doesn't always require presence. Gravity extends from clusters into the void. Light travels through it, altered but unbroken. The void acts without acting. It allows without resisting. It's a physical embodiment of a principle that appears again and again in philosophy and nature alike. That space, absence, and calm are not weaknesses but conditions for growth. In scientific terms, studying the voids also reminds us of humility. The KBC Void, if it exists as described, is an enormous feature of the cosmos, yet we only discovered it recently, and we still struggle to define its boundaries. We live inside it, but it took centuries of measurement and inference to even realize that. The fact that we can't directly see the space that surrounds us shows how limited our perception is. We sense structure through light and motion, through indirect clues. Much of the universe's truth is hidden in what seems invisible. Emptiness teaches us to look carefully at the spaces between, to infer meaning from absence as much as from presence. This is more than a metaphor. The science of voids is fundamentally about reading silence, understanding the structure of what's missing. When astronomers measure the KBC Void, they're not observing bright objects. They're measuring the faint deviations in density, the subtle flows of galaxies, the gentle shifts in redshift that indicate less gravitational slowing. They are studying the shape of nothing. Yet from that study, they extract knowledge about everything. The rate of cosmic expansion, the nature of dark energy, the geometry of space itself. Emptiness becomes the most revealing phenomenon of all. The void also teaches patience. The timescales of its evolution are beyond comprehension. It takes billions of years for its boundaries to shift, for its density to change measurably. And yet, it never stops evolving. The slow expansion of emptiness is as much a part of the universe's rhythm as the fast, fiery lives of stars. In the grand story of cosmic evolution, voids are the long, sustained notes that give structure to the melody. Their constancy allows contrast. Their stillness allows motion elsewhere. They embody the idea that creation and dissolution are two sides of the same process. Standing under a clear night sky, we are surrounded by that lesson. Every patch of darkness between the stars, every invisible stretch between galaxies, is part of the same system that gives rise to light. The universe doesn't hide its structure, it displays it openly, but our senses are tuned to brightness, not to quiet. The challenge, both scientifically and philosophically, is to learn to see the darkness as equally real. The KBC Void isn't a defect in the cosmos, it's one of its defining features. Its existence shapes how we measure distance, how we perceive expansion, how we understand our own position. To live in a void is to live in the most common kind of space the universe provides. Emptiness teaches us that perspective defines meaning. A void can appear as isolation from one angle, as balance from another, and as opportunity from yet another. From within, it feels vast and still. From afar, it looks like a feature of motion, a space being stretched and sculpted by the forces of the universe. Its reality depends on how we look. That multiplicity of interpretation is part of its beauty. The KBC Void doesn't separate us from the universe. It places us within its structure in a way that reveals connection through contrast. Perhaps the greatest lesson of all is that emptiness is generative. The voids of the universe continue to grow, not by consuming, but by allowing, by yielding to expansion, by giving matter room to move. The universe expands because there is space for it to do so. In that sense, emptiness is not an absence of meaning, but the source of it. It provides the room in which galaxies can form, in which light can travel, in which life can wander. Without the quiet, there could be no story. Without the space, there could be no structure. The KBC Void is our cosmic classroom in this regard. It surrounds us with the evidence that silence, space, and nothingness are not voids of understanding, but invitations to it. To recognise that we live inside a vast hollow, and yet remain connected to everything beyond it, is to understand the universe as a balance of fullness and emptiness, of motion and stillness, of presence and absence. And what emptiness teaches us in the end is not how alone we are, but how deeply we belong to a universe that expresses itself through contrast, a universe where even nothing is something worth studying. Thank you for staying until the end of this quiet journey through space. If you've listened all the way here, across the long drift of galaxies, filaments, and the great hollow we call home, you've been travelling through something more than distance. You've been travelling through perspective, through time, through the living rhythm of a universe that expands, flows, and rests in ways that are both immense and intimate. What we call the KBC Void is just one pattern in that rhythm, one breath in an endless cycle of inhaling and exhaling that has gone on for nearly 14 billion years and will continue long after the last star fades. The universe does not simply exist, it breathes, and we, in our small way, breathe with it. When astronomers describe the cosmos expanding, they don't mean galaxies are flying through space like debris from an explosion. They mean that space itself is stretching, carrying everything along with it. The distances between clusters grow, not because of motion through a medium, but because the medium itself is expanding. That expansion is the universe's breath. It's gentle, but unstoppable, the underlying pulse of existence. Over billions of years, it has slowed, quickened and slowed again as matter, radiation and dark energy have taken turns guiding its rhythm. And now, in the age we inhabit, the breath is accelerating, the cosmic lungs filling faster than ever before. The voids are where that expansion is most visible. They're the soft parts of the universe's exhale, the spaces that stretch more freely, the quiet zones between the crowded walls of galaxies. Living in one means existing in the middle of that long, slow outbreath. The KBC Void, with its billion light-year span, is a vast region where the universe relaxes a little, where space expands a little faster, where gravity's grip is slightly looser. We don't feel it directly, of course. On the scale of human life, the void's expansion is imperceptible. But every photon that crosses it, every distant galaxy that drifts through it, every faint redshift we record carries the imprint of that cosmic respiration. The light that reaches us has been stretched by the universe's breath. We live inside the evidence of motion. Thinking of the universe in this way, not as a static void filled with objects, but as a living system that moves and changes how everything feels. The galaxies become like cells in a great organism, connected by filaments of dark matter that act as arteries. The voids are the lungs, expanding and contracting over unimaginable timescales. The clusters are the dense organs, where energy and matter concentrate, where activity thrives. Together they form a system in balance, even if that balance is so vast and slow that we can only glimpse fragments of it. The rhythm of creation and expansion continues whether anyone observes it or not. From our small vantage point, this breath appears eternal, but it has a beginning and perhaps an end. The Big Bang was the first inhalation, the moment when the universe drew in existence itself. Since then, every expansion has been a continuation of that first act. One day, far into the future, the breath may change. If dark energy remains constant, expansion will continue to accelerate until distant galaxies slip beyond reach, their light stretched into invisibility. The sky will grow emptier, quieter, and colder. The universe will seem to fade, though it will not die in any final sense. It will simply settle into its next rhythm, slower, more diffuse, more subtle. In that imagined future, the descendants of our galaxy, if any remain, will live in a sky without visible galaxies beyond their own. They may never know the vast web that surrounds them now. The cosmic background radiation will cool below detectability. The traces of the KBC Void and every other void will vanish from observation, but the physics that governs them will still be there, written into the geometry of space-time. The universe will continue to breathe, though in a different form, perhaps in quantum fluctuations that create new beginnings, or in the quiet persistence of expansion that never truly ends. It's a humbling thought, but not a bleak one. To understand that we are part of such an immense process is to see that life, thought, and observation are expressions of that same cosmic rhythm. The atoms in our bodies were forged in stars that lived and died long before the Milky Way settled into its place inside the void. The carbon, oxygen, and iron we depend on were created by fusion and supernovae in galaxies that once drifted along the void's expanding edge. Every breath we take is part of that continuity. The air in our lungs recycled from generations of stars, the energy in our cells drawn from light that has crossed billions of years of cosmic history. The KBC Void itself becomes less of an anomaly and more of a reflection of how the universe works. It shows that stillness is not the absence of activity, but another mode of it. The regions where space expands fastest are also the regions where time seems to flow most gently. The galaxies inside such regions live quieter lives, forming stars slowly, aging gracefully. The emptiness doesn't isolate them, it gives them space to exist. In that sense, the void teaches the same lesson that the universe as a whole does. That existence is not a competition between fullness and emptiness, but a cooperation between the two. From the human point of view, these ideas are enormous, almost too large to internalize. But there's comfort in scale. The same physical laws that shape the KBC Void also govern the drop of water, the cell, the heartbeat. Gravity, motion, and expansion are universal. They don't stop at the edges of galaxies or the limits of our perception. The patterns repeat in different forms at every level. When you look at the night sky and see the spaces between stars, you're seeing the same balance of presence and absence that defines the largest structures of the cosmos. You're seeing the universe's breath made visible. That recognition changes how silence feels. The darkness above isn't a void in the emotional sense. It's the medium through which everything communicates: light, gravity, time, and awareness. The blackness between galaxies is filled with potential, the same way the pause between thoughts holds the possibility of understanding. The universe's breath is not something happening far away. It's happening through us, in every heartbeat, every breath, every moment of perception. We are part of the same expansion, bound by the same physics, connected to the same rhythm. When scientists map the KBC Void, when they trace the redshifts of distant galaxies and calculate their motions, what they're really doing is measuring the universe's breathing pattern. Each data point is like a pulse, a confirmation that the cosmos is alive with motion. The voids are the quiet intervals that make that motion possible, the soft spaces in which the universe gathers itself before continuing outward again. To live within one is not to be isolated, but to be inside the very mechanism that keeps the cosmos unfolding. If you've been listening for sleep, this is the point where the edges of awareness start to blur. The thought of a universe that breathes, that expands endlessly yet remains whole, is strangely soothing. It takes the sharpness out of time. It makes every worry seem small and temporary. The vastness doesn't erase meaning. It expands it. The same way the universe stretches light, it stretches perspective, showing that even the emptiest spaces are filled with process, purpose, and motion. There's no final discovery waiting beyond the void, no ultimate boundary to reach. The cosmos doesn't end. It transitions layer by layer into new forms of the same underlying energy. The KBC Void is one chapter in that continuous transformation, one open breath among billions, and here, in this moment, we're inside it, listening, observing, part of the stillness and the motion at once. So if you find yourself thinking about the emptiness tonight, try to remember that it isn't emptiness at all. It's the quiet half of a universal rhythm. Every expansion is followed by calm, every silence followed by motion. The galaxies drift, the light stretches, the void expands, and through it all the universe continues to breathe. And as it does, it carries us with it, gently, endlessly, through the spaces between stars, across the walls of time and into whatever comes next. One slow, steady breath at a time.